remains fixed all the time. That is what the present technology can do. So when you are out, then this beam can become very harmful for you. I have discussed these situations in my invited paper at the University of Trento, Italy in the year 2016. I was one of the earliest proposers of a practical network system. Now, what I proposed was that there should be a two-tier network topology. In that two-tier network topology, what will happen is that the macro transmission tower will actually communicate with, say, a picocell or a microcell. And this picocell and microcell, this communication will be the tier 1 communication. So this is no direct communication between the main tower and the users, unlike the present situation where the tower directly communicates, the main tower directly communicates with you. Okay, so I proposed a situation, a two-tier topology, where the direct communication between the user and the tower doesn't take place. Instead, what happens is the main tower, the macro tower, communicates with the micro tower with the massive MIMOs. So the beam formation is between the micro tower and the macro tower. And that will provide the necessary multiplexing. There will be several such, instead of users, there will be several such micro towers or picocell towers, which can directly communicate with the main tower. This is the tier 1 arrangement of the communication. So here you can imagine that one of these micro towers or pico towers is a group of users, because each such micro tower handles, say for example, around 100 people. And so the 100 people, on behalf of these 100 people, the beam division multiplexing is done from their own tower to the main tower. Whereas the pico tower by itself, when it is transmitting to the users, they are no direct beams. They are the same kind of communication that had been done earlier with 4G and 3G, where the waves are spread all around so that anybody can receive it. There is no space division multiplexing within a microcell or a picocell or a femtocell, so to say. And you don't need to be, because there are very small cells, and now the millimeter waves or microwaves, they do not face the kind of attenuation that we talked about when the towers are very far away and there are buildings in between. Okay, so in that way there can be a backward compatibility, and we can get rid of the harms of the electromagnetic, high power electromagnetic wave transmission as well. Needless to say that these pico towers are not going to transmit as much high power as the macro towers would. So that is the case, and this is the simplest two-tier network topology, where in the first tier the macro tower communicates with a micro or a pico or the small cell tower, and within the small cell tower the transmission is ubiquitous, and we can get rid of the harms of high power transmission. I should also point out that this is not a good idea to say that high power microwaves or millimeter waves cannot harm because they are non-ionizing. As I was talking about, that even a DC of 2.25 watts can ionize water, and more than 70% of our body is water. So, and there is a lot of more research to be done, that what are the harmful effects of microwaves. Some of those effects on cell division and cell multiplication is discussed in this paper. It's an important paper that you can always go through in the IEEE library. So now, before we can talk about anything conclusive here, let us see what people have to say and ask. Okay. So let us take up some questions. Dr. Mishra, if you can tell me about some of the questions that you have received. Hello.
Yes, sir.
Huh.
Sir, there is one question. What are the
Yeah.
5G challenges while designing?
Okay, so this is like the design challenges what Dr. Mishra had been talking about, right?
Yes, yes, yes. Yes, sir.
Any more questions? Any more
No,
questions?
no, no, sir. No further questions till now.
No more questions. Now, I'll take up some design challenges, but some are already discussed. Let me tell you what are those. So, there is always a design challenge regarding the multiplexing that I talked about, you see. Since phased array brings in new multiplexing technique, that is beam division multiple access, there are a lot of design challenges within this. Now, usually the arrays which were used before, the phased arrays which were used, were not multi-beam configuration phased arrays. Okay, they were usually single beam configurations used in radars, and where a beam tracks a particular target. And multi-beams are a specialty. So this is always a design challenge, that offering the same frequency, same time, you generate different beams through the same antenna array. This is a particular challenge which the phased array engineers face. It's not a challenge, but rather I should say it's a kind of optimization challenge, that how many beams you can, within the same array, how many beams you can facilitate. Of course they exist, but what are the different ways you can optimize those? So that is one of the challenges. And the second thing that I talked about is that within, say, for example, a non-orthogonal multiple access technique, you have to develop several interference cancellers, like I talked about, a successive interference cancellation. Now, when we do the successive interference cancellation, this is a scheme which is proposed but not yet implemented in 5G. What does that mean? That means there are several design challenges within this. So if you can actually, with this logic of successive interference cancellation, you can take up the precise design challenges regarding the phase lag and regarding the signal to noise ratio, how to optimize these two factors, signal to noise ratio, as well as the phase lag between them. And then you can design a very good SIC. So SIC remains a design challenge within. But the major player within 5G, as you can all see, is the massive MIMO or phased array. This has been directly used. It is in use with all the 5G deployments so far, and certainly that 5G deployment will take up the MIMO, the successive interference cancellation issues as well. Okay, so I think I'll take up more questions after I finish off my presentation. I think that would be a better idea, so that whatever I want to finish can also answer some of the questions which are already asked, and I'll take up those afterwards, right? Okay.
Yes.
Okay. Now, what can we conclude so far? Antenna arrays or massive MIMOs are the major technology enabler for 5G and beyond. Now, this is a very important factor that we must understand here, is that when 5G came in, we started talking about massive MIMOs, antennas. Antennas became all of a sudden a very important factor. I think by this time you might have realized why is that so? Because these antennas are the major driving factor of beam multiplexing that we talked about. Antenna arrays rather, not individual antennas, but antenna arrays. And some, of course, individual antennas have their own role to play in it. But in totality, the antenna system of many antennas, a system of antennas called arrays, has taken up the major initiative in the technology change. We don't talk about, a 5G mixer, a 5G modulator, a 5G amplifier, so on and so forth. What is the reason? Because in the 5G, those devices are not logically different. Whereas in antenna arrays, when the antenna arrays were brought in, massive MIMOs were brought in, the beam forming was brought in, they were logically different from what had been done earlier. But with other things like the amplifier, logically remains the same. There are no new components except for the fact that now we want to have amplifiers which can handle a higher bandwidth of millimeter waves. Similarly, the mixers. Similar, any other factor, for example, the individual antennas or the filters or whatever. So they all are actually the same, logically the same. What has logically changed is the multiplexing technique. One is that now we are using space division multiplexing more in the form of beam multiplexing. Second, we are on the verge of using successive interference cancellations, and we call it a power NOMA. This is the most promising candidate of those. So a power NOMA, power non-orthogonal multiple access. This is another candidate which is logically different. So people talk about NOMA very much in different papers that you see. Non-orthogonal multiple access techniques. So this is going to be the future prospect of communications, that means beyond 5G. And also the phased arrays have to do a lot about the current topology and all these things. And as you can see that the phased array now, they do not directly communicate with the users, but rather they communicate with a micro. So there's a phased array communication between macro and micro towers, macro and the small cells. And small cells by themselves transmit and receive from the users ubiquitously and not through beams. Okay, so and that is the reason you see the speakers who you have got today. They're almost all talking about antennas and nothing else. So there is nothing wrong in that. Just because of the fact antennas are the major enablers in the 5G communication and beyond. Of course, we should also talk about non-orthogonal multiple access techniques as well, but due to the limited time, I cannot cover everything in detail. Okay, now let us take up the next point. Some of the newest technological breakthroughs are based on some of the oldest inventions. As we could see that this 5G has been enabled by the inventions of 1916 and 1894. So they are so old. So what this means, of course, there's nothing wrong to bring in the old technology, the old inventions, at least using them in a better way. But we could have done it earlier, right? Now the point is that why can't we do it earlier? Because I think one of the primary reasons is that today's researcher is actually not doing genuine research. We almost, and it's not just about India, I've seen across the world, people are after fancy research things. So if something, say for example, wireless power transfer, energy harvesting. So if that is there, people are running after it, writing piles and piles of papers without thinking the practical aspect. So we have reduced ourselves to our comfort zones of not thinking anything new. We don't bring in new technologies. Whatever new technologies, they're all based on old things, old inventions. We don't invent anymore. We just point out some used cases. Okay, so the old inventions have been used in a new application. That is what we can do. So we are finding new applications for the older inventions. We're not making some genuine invention or innovation these days. I'm quite sad in that way. I've been in academics. I've been teaching for the last 20 years, but the same thing prevails, and not just in India. I should say it's not that we as Indians don't do it. It's across the world the same thing. It's a kind in the Hindi we call it a bhed chal, so that the bhed chal is also prevalent among scientists. Without giving it a thought, we do a lot of research. that is immaterial and that doesn't have practical use. So you see, Government of India also focuses these days on the kind of research that we do. We being engineers should take up research that is practical. No, we shouldn't. We should leave our comfort zones and do things which are practically relevant. And since we are engineers, we are not just theoretical researchers, we are practical researchers. So we must try such theories which lead to some practical aspects. And another very important thing for a development, since this is a faculty development program, another very important thing is for the real development, we must find our own research problems and own research solutions. Let us identify our own problems, not just don't sit back and see people define problems and solve, and you find a place in between them so that you can do some mumbo jumbos and come out with just a paper which doesn't have a practical implementation. So just don't go after papers, and we should concentrate on genuine research, find your own problems, own solutions. You'll be more confident, you'll be more meaningful. Of course, this is just a suggestion. Whatever you wish, you can do such. Okay. Anyway, so another aspect is old to new, Indians have always been at the technological forefront. As you can see, whatever we have discussed so far, at least out of the 4 contributors who I discussed, 2 are Indians. One is Professor J.C. Bose, another is Professor Dinesh Baradia. So you see that Indians have a lot to contribute in the forefront of forefront technology, cutting edge technology. But we do not realize it. Sooner we realize it, the better it is for us. The sooner our government realizes it, it is better for it. And sooner the world realizes it, it is better. Because I would suggest that the world invests more of its resources and time with the Indian technocrats. Because unlike the neighborhood of India, we are genuine researchers who create technology and not steal technology. So it is very important that we are given as a technologists, we are given a chance to serve and the frontier research more and more. And another thing is that I would like to say, all of you. And also, I want to communicate this message to the government as well. We have talked about Make in India, but this Make in India is like a feature where cheap labors can be used. Foreign technology comes in, and the cheap labor of India is used to do something for the industrialization purpose. We should not be just reduced to Make in India. We should actually think about create in India, ideate in India, design in India. That is what our motto should be. So that the intellectual property which we have should come in focus, because that is better than others. Anyway, so let us just go ahead and take up some of the challenges, talk about some of the challenges of arrays, MIMO arrays, because these are the prominent ones that is in research, and the problems which I solved as a researcher. I would like to talk something about those. So, of course, before that, there is another thing that we can see just to make the situation a little lighter. We again come back to the point of game of greed. So, will this greed ever end? Because you see, at any given technology, as I said before, that we are restricted by the bandwidth. And with the same bandwidth, if the service provider or the entrepreneur wants to earn more, he would pour in more and more users. Okay? So certainly, per user bandwidth reduces. And this is going to happen in any new technology that we are going to produce. So you see here, the entrepreneur is offering free 5G to a beggar. And beggar is freely using it. So he knows it's offered free, so he doesn't have to worry. But the problem is that if you offer a beggar a bottle of whiskey free of cost, he will make sure when he gets addicted to it, he will make sure that whether he can earn his living or not, he can earn a bottle of whiskey every day. So it's a kind of addiction that, even the new technology of 5G or 6G or whatever is going to come up later, that is going to create. It's a kind of addiction. So people later on with the free period of offering, the addiction is developed, and after the addiction is developed, then they are forced, in a way, with the situation, with the addiction, they're forced to pay for it. So a beggar, how poor he is, he would pay for a fag of to fag a bidi or a cigarette, in whichever way he can. And he may not eat just because his addiction becomes more important. So anyway, this is one of the cynical aspects that we are looking into. There are a lot of great things with the 5G technology and the future technologies that we're going to have. But this is a kind of another view of the coin. Okay, so is the 5G a permanent solution? Certainly not. We are going to have a 6G, 7G, 8G, and whatever we can talk about in future, and there are always scopes of betterment. So let us see what betterment can we do. Our greeds continue. Some can be addressed, you see, and some cannot be. For example, when we say, I want to control everything with my phone, of course it is possible. I want to use my phone underwater. Oh, well, so can you even breathe in there? So you cannot breathe in there. So you're talking about using your phone underwater. So there are situations, you see, where your demands can be met, and situations where they cannot be. Similarly, you can say, I want to use my phone while hanging upside down and lying down and whatnot. So the real question posed to the engineer is, do we have isotropic antennas? Because such kind of a situation, when you're lying down or you are inverted, you need an isotropic transmission, all around transmission and reception. Do we really have that? So, and I want to drive my car to the moon. Of course, this is not to the wireless engineer, but in general, there are such fancies which exist. So we have to ask ourselves a question: did you try the Everest first? You first drive to the Everest and then talk about the moon. Okay. So our current demands from 5G and beyond, in a nutshell, that is, I've talked about it, but let us recapitulate it in a nutshell. When this video is played, I'm going to mute myself so that you can hear this video without any echo. So just for the sake of this video, I'm muting it, okay? Muting myself.
"5G is the fifth generation of wireless data networks, and it will improve them far more than 4G or 3G ever could. You'll feel it in your phone, your home, your car, and in the city and town around you. Downloads and streaming should happen literally without delay. Cars will talk to each other to prevent collisions. And untethered augmented and virtual reality can finally be achieved with real-time response. Not to mention industrial benefits like remote surgery or drone control. 5G does its magic with three key abilities. First, high bandwidth. 4G could only muster about 200 megabits per second of data throughput on a good day. 5G can handle up to 1 gigabit or more. That's 1,000 megabits a second on up. Low latency. 4G suffers from around 100 milliseconds or so in response delay or latency. 5G reaction time can be as low as 1 millisecond, which makes everything happen virtually instantly. And dense connections. In a given square kilometer, 4G could only manage to connect about 1/10 the amount of devices as 5G can. If that's some of what 5G does, how does it do it? 5G uses new radio technology, the part of any wireless device that makes the connection. 5G uses some radio frequencies in a band known as sub-6, from 600 megahertz to 6 gigahertz, part of which is also used by current 4G LTE. But 5G will also use a higher band of radio frequencies, from 24 gigahertz to as high as 86. These much higher frequencies bring with them much higher data rates. Now, while these new 5G radio waves can carry more data with higher performance, they can't carry it as far. So 5G will use a lot of so-called small cells. These are small versions of the big cellular towers we all know. 5G will also use some new tricks in these small cells, like beamforming, to efficiently aim transmissions rather than just spray everything everywhere. The bottom line, though, you will need new phones, tablets, portable hotspots, and the like with a 5G radio inside to connect to the new 5G networks. Your current 4G or even 3G gear can't tap into it. 5G networks will also position more data and computing resources closer to you that will avoid blunting 5G's low latency benefits. Most of us do think of phones when we think of wireless networks, but phones may actually be the least interesting thing about 5G. It will also power autonomous cars, so they have awareness of every other car, bike, pedestrian, and traffic signal around them. Smart cities based on 5G can make almost anything that's electric also connected and aware. When a bridge needs repair, why can't it tell someone? With a mesh of 5G connected sensors, it could. And then there's your home. 5G will offer a new way to get internet there, eschewing cable or DSL, and one day maybe even obviating your Wi-Fi router altogether, as devices may just use 5G natively to connect directly to a wireless ISP. 5G has renewed concerns about the safety of cellular radio waves. Some cities have taken action to block 5G deployment. Health questions come up around 5G's use of microwave frequencies, lots of them as we've seen, thanks to that large number of small cells that will be installed around us. Now, while 5G may sound like a lot of microwave ovens mounted on poles running with their doors open, in fact, microwaves are nothing new. Already emitted by your current smartphone, old cordless phones, your wireless headphones and earbuds, and just about anything with Wi-Fi, as well as, yes, microwave ovens. But even 5G's highest frequencies are considered by scientists to be non-ionizing radiation. You have to move on up to X-rays, gamma rays, and cosmic radiation to find the kind of emissions that will harm cells, and 5G is far below that. 5G follows the inverse square law, losing power rapidly at even a small distance from the small cell. The US CDC says there is no scientific evidence to provide a definite answer to the question of cellular radio wave safety, whether it's 3G, 4G, or 5G. 5G will take years to roll out and some investment on your part, but the complexity of that deployment and debugging should be worth the wait, delivering the world we've been promised for a long time, where everything is connected, aware, and responsive, and a world in which we can stop worrying about the availability or performance of connectivity in the first place.
Well, hope you enjoyed this 5-minute video. It has been produced by CNET. It's quite a popular site where you get to download a lot of new softwares. Hopefully you are aware of it. And they have taken an initiative to popularize 5G. Anyway, so you might have heard that they're talking about this ionization of ionization radiation, which they talked about. I also did, and I told you that this is not such a simple factor that you categorize something as ionizing and something as non-ionizing. Anyway, let us just go ahead with this and see now that what are some of the design challenges that we must take up in future, and these design challenges which were rather taken up by me and people do not know about it. Okay. So let me, okay, this is, so this is some challenges and solutions for next generation communication. Now, as I can see in one of your presentations that's going to take place today, or maybe in some of the sessions ahead, is electrically small arrays. Electrically small antennas, that's the presentation. But you see that the more important factor here is not the electrically small antennas. But we must be able to reduce the size of the arrays, that the big massive arrays which have hundreds of antennas, for example. So we must be able to reduce their sizes as well. Okay, because with 5G we are not using individual antennas. So individual, more than the sizes of the individual antennas, their overall size of the system matters more. So this is one of the design challenges. Now, why do we need to reduce the size of the antenna? Because they're inconvenient. Now, for example, at one time, instead of 100 antennas, you need 1,000 antennas to create sharper beams. Let us say, for example, we want to create very sharp beam, and for that we have increased the number of antennas, and that is what happens. With higher number of antennas, you can increase the sharper beam width. So a very high resolution beam can be created, a very high resolution space, a private space can be created in the space with the use of a large enough number of antennas. So they can always be in demand. Maybe in one day we want denser and denser beam division multiplexing. We would rather want to increase our number of antennas than the present day's usage. Okay. So, but with increase in antenna, we will increase the size of the system. And maybe such a big size of system cannot be mounted over the rooftops or a tower. So like everywhere, you cannot just put up a billboard size antenna. So that can become not just inconvenient, but it may not be practical, because there's a lot of air drag which can blow the antennas off their roots. So there are a lot of factors that we can think about. So there's always a requirement of miniaturization, as we are miniaturizing our circuits and everything together. So electrically small arrays, like electrically small antennas, we would also want electrically small arrays. But what is the design challenge here? That has to be looked into. Okay. So the design challenge is that when we are using these antennas, we have the antennas kept close to each other, definitely, but can we just stick one antenna with another in an array? Certainly not. So there is a problem called mutual coupling. When one antenna is kept near to it, if it is kept nearer than lambda by 2, half the wavelength that it is operating with, if it is kept nearer than that, then there's a phenomena called mutual coupling between them. And this mutual coupling disturbs the radiation pattern that has been created. So instead of the main beam, there are side lobes which can almost pose like the main beam, their powers get increased. Okay? Just like here, as you can see. Can you see this? That in the main beam, due to mutual coupling, the side lobes have risen up. Okay? Side lobes have risen up, and this will actually create a kind of noise, side lobe interference for the transmission, so to say. Okay. So now this is a problem. So you cannot reduce the array size by reducing the inter-element spacing beyond lambda by 2. This is the present day situation, and you can see one of the talks that you have scheduled is on isolation of antennas. This is all because of that. So there are people that are still using antennas, these techniques of isolation techniques, so that when the one antenna is kept closer to each other, there kind of barrier is being put, or frequency selective surface is put, so that one antenna doesn't couple its energy to the other in the near field. Okay. So that is one of the problems which the world is still dealing with, unaware of the fact that I have solved this problem back in 2016. Okay. Now, this reference that I am giving of my paper in 2006, the reference number 6, it has been published in 2016 in the IEEE Transactions on Antenna Propagation. Okay. So in this method, what I do is, now there is no need for any kind of isolation technique between antennas. They can be kept as close to each other as possible, And you can keep lambda at a distance of lambda by 4 or lambda by 8 if it's individual sizes permit. You can keep them as close to each other as possible and still get rid of the effect of the mutual coupling. The radiation pattern can be corrected back to the one which is without mutual coupling, as you can see in this particular graph, where you have a desired pattern which is seen in blue marks. Of course, since it is covered with the corrected pattern, you can't distinguish it very clearly. The reason, because it has been perfectly matched. So earlier, the uncorrected pattern is the black dotted pattern. So with my technique, which I called parametric assimilation technique in this particular paper, any amount of mutual coupling effect on the radiation pattern can be corrected by the use of this technique. So the pattern has been corrected back. Now what you can do is you can miniaturize these electrically, miniaturize the entire array without any worry with this radiation pattern corrector. Okay, and the isolation between antennas are no more required, but still there are researches going on and still people publishing on isolation of antennas. This is what I was trying to point out. We are after a particular research. We are satisfied in our comfort zone. We don't look around what is being happening, what has practically happened, and we keep on doing our research and don't even bother whether this carries any practical meaning or not. Okay, so this is one of the significant research that I contributed towards next generation communication in massive MIMO technology. Another one which I did was wide banding of arrays. This is very important, you see. Now we are talking about very wide band. We want the antenna array, individual antennas, as well as antenna arrays to progressively use wider and wider bands. Now millimeter wave bands have also come in, you see. So bigger, larger and larger bands. Now, is it possible? Is wide banding always possible? Now you see, there is a phenomena in arrays which is called grating lobes. Well, what happens is, grating lobes appear when you are running a particular antenna at a frequency double than the design frequency. Suppose an array is operating at frequency X. If the frequency of operation becomes 2x, there are grating lobes. If they become 4x, there are still more grating lobes. Okay? So, and these grating lobes are equivalent lobes than the main lobe. Now, if you get an equivalent main lobe, then how do you actually multiplex it? Because there are several beams, you do not know which one is the main lobe. You won't be able to multiplex with a single beam. The whole private space. There are several private spaces which have come up due to this grating lobe phenomenon. Are you able to understand this? Now see, so there needs to be a technique for this wide banding and suppression of grating lobes. Fortunately, one of my papers, again, in year 2016. Now, even if your frequency becomes 4x, you see, these are the grating lobes created, and with this blue line, I have suppressed the grating lobes using a technique called hard windowing without any kind of sophisticated equipment. It's just the placement of antennas which made this difference. You see, the grating lobes are suppressed, and you can, and this is it is even here where it is not zero. Here it is zero. The grating lobe is zero, and here it has been suppressed below 80%. So of the total power. This is a very good thing without any complicated design equipment, without any kind of beam forming network. This could have been achieved by a technique which I invented called grating lobe technique. And you people are free to use this research and further this research. Of course, commercially this cannot be utilized just because of the patents which I have filed. But for an academic research, you're free to use this in different kind of researches that you want to do. Okay, so these are the two design challenges which I took up, and there are many more which I'm taking up, but the time will fall short to discuss about these. Let us look into the references. Kev Brown, electrical oscillations and wireless telegraphy. That is what I talked about, the phased array being invented for the first time. Dinesh Baradia, he presented this in a conference paper. ALC Hui, he has this transaction and communication. This is about the successive interference cancellation. Then, if you want to know more about J.C. Bose and his contribution of millimeter waves, you can look down into my article, that is History of Wireless Communication and Evolution Through Time and People. And then this is the one which I was talking about, that I have contributed some of the earliest ideas on what should be the network topology. This was an invited paper in the Smart Cities Conference in Trento, Italy in the year 2016. Antenna system strategies for wireless sensor networks in resource-hungry smart cities. This is what the topic was. But the topology we discussed was in general applicable to 5G as well. Okay. Now this is the sixth reference where my paper got published in IEEE Transaction on Antennas. This is radiation pattern correction in mutually coupled antenna arrays using parametric assimilation technique. This is what I was talking about a short while ago. And then the last one is again the grating lobe suppression. This was published in IEEE Antennas and Wireless Propagation Letters in the year 2016. So what people have not yet done was done by me in the year 2016. Okay, so it's almost 5 years back. So all my technologies which I invented, which I contributed, hopefully can be utilized in next generation. They couldn't be utilized in the 5th generation, but hopefully they will be implemented in 6th generation. So I'm now open for questions. Please do ask me some questions so that I can answer them.
Thank you, sir. Thank you, sir, for this wonderful session on the modern devices and techniques for the next generation wireless communication. In this lecture, you covered, you started your lecture with the creative concept that is a greedy tug of war between the bandwidth and the users. And you covered in your lecture 5G new radios and multiplexing techniques, covered power NOMO concept and power stream concept of power stream, new bands, 5G bands, and the new architecture of this bands challenges and solution for the next generation. So this will be very helpful for the new researchers. This concept behind your concept of your lecture, behind this lecture is very helpful. I hope this will be very helpful for the researchers. So I have a few questions in the chat box. I will read one by one.
Yes, so, please do it.
So the one question is from the Karthika. How spectrum allocation in 5G system varies from existing spectrum allocation?
Well, as I already told, that the variation is just in the case of the millimeter waves. The 4G and below, they did not use millimeter waves, but here we do use millimeter waves. As I can see, I can show you again, back again here, where. So let's look into that slide. Here. Here it is. Okay. So have a look at this slide. So there are three major bands in 5G. The FR1, that is from 450 megahertz to 1 gigahertz. Now, goes without saying that this is already being used in 2G, 3G, and 4G. Then it becomes the mid band. Low band is FR1, that is 450 to 1 gigahertz. Mid band is 1 gigahertz to 7 gigahertz. This is being utilized by 5G, 4G, 3G, and 2G. And particularly for the 5G, we have the millimeter band, 24 gigahertz to 52 gigahertz, which is being used by 5G. Okay, and primarily this band will be used for and is being used for the tower-to-tower communication that I was talking about, macro to micro cell communication, macro to small cell communication using beamforming. This is the particular thing that we are going to use in those beamforming applications, right? Yes, hopefully I satisfied the questioner about. Hopefully this satisfies the question.
Yes, sir. So next question is from Gauri Shankar Sharma. It is about the MIMO antenna. How to improve diversity performance of MIMO antenna?
Well, diversity is the beam forming that I talked about. You see, more and more distinct beams that you can create increases the diversity. That is what the diversity is. Okay. So more beams you create within these MIMO arrays, more the diversity is, right?
Yes, sir. Next question is from the Narayan Rao. Why millimeter wave is chosen for 5G?
What? Come again?
Why millimeter wave is chosen for 5G?
Because the rest of the bands are already preoccupied. We don't have any more space, see?
Okay.
So we were already running out of this bandwidth space. We wanted more users. We want more bandwidth. What can we do? We have to find some new band areas. So this is the one we could spare, because between millimeter waves and the earlier bands that we were using, this is occupied by satellite communication, defense communication, and all these things. So what is available to us is the millimeter wave band, unused band, which can be used now. Okay, so millimeter waves were very sparsely used in defense and satellite communications earlier, before coming to 5G, right? So we have enough space in the millimeter band to be used for commercial telephony. That is the reason we are using millimeter waves. Rest of the bands are already occupied.
Okay, sir.
Yes.
So next question is, what are the parameters which we need to concentrate more in 5G?
Well, as I told you, yes, this is and parameters in the sense, hopefully he wants to ask about the design parameters. Okay, so
yes.
Design parameters, as will be also discussed by a few of perhaps in the coming sessions, that we have to, for individual antennas, we need to reduce their sizes. Individual antennas, that is one. We need to reduce the size of the array as well, which is addressed by one of my inventions, but the radiation pattern corrector that requires a complex set of amplitudes and phases, and there is called a beam forming network. We must understand that. So only the antennas doesn't serve the purpose. Behind it, there's a signal processing aspect, and this signal processing aspect is done by a beam forming network. Both in receiving mode we call these smart antennas, and in transmitting mode we call them phased arrays. Okay, so in transmitting mode or receiving mode, we need a beam forming network which can generate beams in one direction, multiple beams in several directions, and which can receive multiple beams from several directions, thus making this beam multiplexing successful. So a lot goes into the signal processing part. Very less research is being done in our country about this beam forming network. So we must look at this particular parameter, if you call it a parameter or aspect. So this aspect needs to be concentrated on. And then of course successive interference cancellation. How do you make it? And there is a factor called PAPR, peak amplitude to power ratio. Okay, so average peak to average power ratio, PAPR. Okay, so this is the aspect when we design, say, amplifiers and we mixers, we try to reduce this factor. So there are different design parameters that we take up in different hardware designs. And of course, the modulation techniques, there are nothing new in it. We are using the same QAM, we are using QPSK. Those are the modulation techniques that we are using. So for the multiplexers, we need new design and multiplexers in SDM domain, they are the antennas that we are talking about, and in NOMA domain, we are talking about this power NOMA and all these things. They need sophisticated designs, and where we have a very good resolution between the phase lags and the one which can have a very balanced signal to noise ratio. So those are always a design challenge throughout the ages of communication, whether it's 2G, 3G, 4G, or 5G. Hopefully that answers the question.
Yes, sir. Yeah. So next question in the chat box is millimeter is licensed or unlicensed?
Well, a lot is unlicensed and a lot is licensed, and it depends upon which country you are in. Okay, so so there are licenses being created in the band. The band is very large. It can go up to say 100 gigahertz and 500 gigahertz. So there are lot is not in focus at all. So you can do a lot in the millimeter bands, and that's the reason we are focusing this band, because it is unutilized band. A lot will be available for free usage in your local area network as well in near future. People are working on that. So be rest assured, a lot of that band will be also freely available for you for your own experimentation, just like the free band that is used in the Bluetooth range that is available for you to do free, like 2.4 gigahertz, 5 gigahertz. If you use lesser power, you can use it freely in your home, the Bluetooth or the Wi-Fi. It is the free band, right? Since it is free band, you don't have to purchase a license for your Wi-Fi spectrum. Do you purchase it? No, because it is freely available. Similarly, in the millimeter domain, also the unlicensed bands will be available for sure. Yes. Any more questions?
One is asking about best suitable antenna for 5G.
Suitable antenna? Any antenna that radiates is suitable. Okay. But one thing that we must understand is that here individual antennas have a limited role to play rather than the antenna cluster. And we are talking about arrays here, not individual antennas. Now, since we are talking about arrays, and we also are talking about beam steering. So the beams that you are generating may not be fixed, it can be steered in different directions. Now what happens is that usually an individual antenna doesn't have an isotropic radiation. That is impossible, okay, till then. So it usually radiates in omnidirectional pattern in some cases, like the dipole, okay. So the omnidirectional plane, if you utilize that plane, it will have a 180-degree scan angle. But if it is not an omnidirectional antenna, the beam space is restricted, so the scan space also gets restricted. So the antennas that we use for these arrays, we should focus on omnidirectional antennas for the massive MIMO users. Otherwise, your beam space gets restricted, and you can scan up to say 60 degree or 40 degrees or 50 degrees, and it cannot be 180 degrees that you want for the phased array to operate on. So a very important factor is that your individual antennas should be radiating more and more uniformly around you. Those are the kind of antennas that you require for 5G and next generation communication, because they are going to be implemented with the antenna arrays. And that is what the antenna array demands, that you can, so that you scan them in any direction possible with equal power. Yes.
So, one person is asking that millimeter wave had more attenuation. So to overcome this, we have to increase the power. And to increase the power might harmful to human. So
yes,
what we have to do for this?
That is what I already said and discussed. See, that in a two-tier topology that I am proposing, and that has been implemented, practically that is the implementation. I proposed it in 2016, but that is what is practically implemented now. The direct beams do not come to you, so they are not as powerful. In a small cell, say a pico cell or a femto cell, the power is spread all around, so the effective power that is reaching you is lesser, okay? Whether it is millimeter wave or any other wave. So you can be rest assured that the power is no more harmful to you, okay? So unless a direct beam comes to you, the power is not going to be harmful. The moment a direct beam, the network is so designed that the direct beam comes to you, it can be harmful to you, right? So with this kind of a two-tier design where you have a macro cell and a micro cell, small cells, and the high power communication, that means the beam-to-beam communication is happening only between the macro cell and the small cell tower. That is where you are not in there. You know, you are not communicating that point-to-point communication. That's a line-of-sight point-to-point communication. And when within a microcell, there is no line-of-sight communication. It is the usual communication that we're having, the low-power communication. Okay? Does that answer the question? Hopefully, that does.
So last question is, sir, can you suggest cross-polarization reduction methods in FR2?
Well, I think this is beyond the scope of the presentation. I can suggest, but if I get into an antenna design there, okay, because you cannot just pop up with an answer without introducing different things. First of all, people would like to know what is this cross polarization. for a communication person, this is quite new thing when you talk about polarization of antennas, because the communication engineer talks more about multiplexing, more about say modulation and signal processing and so on. So if you want me to talk about different design aspects of antenna using and also polarization, cross polarization, you invite me over for a different session at a different time. I'm sorry that maybe some of the other speakers, because they are all on antennas that I can see. Yes, so you can pose this question to some of the other speakers. But this is not the right presentation, because I have not presented a background on antennas, a proper background on antennas which can deal with cross polarization. Although I specialize in that. Although I specialize in that, but I didn't present that. Anyway, so.
Thank you, yes, sir. There is no more question. So
okay.
Thank you, sir. Thank you for this wonderful session. Thank you very much, sir.
Thank you so much. Hopefully you have enjoyed it, and hopefully I could answer all your questions.
Yes,
but
definitely,
in general, I would reiterate that all the researchers don't be in a hue and cry to publish more and more papers without thinking about the practical aspect. Define your problem, define your solutions, and you will be and go have a fundamental approach.
Yes, sir.
When I was in Bombay in one of the colleges, I was teaching second-year students, and I saw a video of an IIT Kanpur professor defining the signal. I found it wrong. I wrote an article. It got published in the highest platform, the Signal Processing magazine, that has an impact factor over 11. Okay, so now the definition of the signal is changed. So what I think is that my fundamental approach, the critical thinking, that has helped me a lot in doing very significant work in the world. And I got recognition from all around. There are people who know me, I collaborate with around the world. So I think if you just keep this approach, this kind of approach, just don't be after publishing papers. I want more and more paper, people will appreciate me. No, that's not the case. You have a single paper with worth the go. You just do it. Let you have just one paper that can change the world, rather than hundreds and thousands of papers which can't do any shit. Okay, so that is what my take on whatever I want to say. Okay, thank you so much.
Thank you so much. Thank you very much
for having me.
Thank you very much, sir. Pragyan sir, thank you very much for accepting our invitation.
Thank you so much. It's my pleasure. Namaskar.
Oh, dear participant, we are having the second session. So,
dear participant, due to the health emergency, the scheduled speaker are not available at present. Initially, Dr. Chinmay Saha was the speaker for the second session, but due to the health emergency, we shift their session with on Wednesday, and Wednesday second session was shifted today. But that speaker also have some health emergency, so they will join I think around 1:15 because we do not have any control on that medical emergencies, so we have to consider it. So meanwhile, though I am not prepared for this presentation because my role was the coordinating this FDP, but since there is medical emergency with the speakers, hopefully they will join at 1:15. So for half an hour, I'm showing my work. So it may be helpful to you. It may be helpful to the beginners. So am I audible to all of you clearly?
Yes, sir. You are very much audible.
Yes, sir.
My screen is visible to you?
Yes, sir. Yes, sir.
So I'm going in a... So I have worked on a cylindrical dielectric resonator antenna. So topic of my work or topic of my presentation is study and design of the cylindrical dielectric resonator antenna, case study for the X-band frequency application. So as we know that the X-band frequency range from 8 gigahertz to 12 gigahertz. So I have designed the antennas for this frequency. So these are the contents of my presentation. First, introduction of antenna, introduction of...
Excuse me, sir.
Huh?
Mishra, sir, your slide is not moving as well as it is not in the full screen mode.
But here it is moving.
So,
Take just a minute.
yeah, now
Yes,
now
now-
it's moving.
So when I am going in a full screen mode at our end, then it is not moving. So it is visible to you?
Yeah, it
Yes,
is.
sir.
It is
Okay.
now.
So, so contents of my presentation is introduction of the antenna, that is the cylindrical dielectric resonator antenna. What are the motivation behind the proposed work? What we have done in our PhD, and conclusion, and then references. So, as we know that the wireless communication is shifting towards microwave and near millimeter wave frequency side to meet the requirements of the emerging broadband and ultra wideband systems. So as first speaker has told that we are moving toward the millimeter wave frequency to work at the 5G communication system, because already the lower frequency band is already congested, and this X band frequency is devoted for the satellite communication and radar communication. So ultimately we have to move toward the higher frequency sides. And as per the knowledge of the communication system, we know that the channel capacity is given by the bandwidth log 1 plus signal to noise ratio. So for getting the better channel capacity, means high data rate, we have to move toward the system which can provide the higher bandwidth. So which can provide the higher bandwidth when we are moving toward the higher frequency, means microwave system or millimeter wave system that can provide you the large bandwidth. So that will directly enhance the channel capacity, because other factors are either you can increase the signal to noise ratio, because but we have limitation that we cannot increase the signal power beyond some certain limits, because it will introduce some health problem. Also we cannot radiate the 5 watt or 10 watt from our mobile system. So that's why our mobile system works at the lower power, because we are continuously interacting with our mobile. So that's why we cannot increase the signal to noise ratio after some certain limits. So what are the option? Option is that we can increase the bandwidth of the system. So how we can increase the bandwidth of the system? By moving toward the higher frequency sides. So that's why the communication system or wireless system is moving toward the higher frequency sides to satisfy the requirements of the users. And what are the requirements? We need high data rate, we need low latency, and that can be provided if we will move toward the higher frequency sides. So as we know that the basic fundamental that the antenna length should be the comparable with the lambda by 2, means if we are moving toward the higher frequency side, means our dimension of the antenna will decrease, because we know that the C is equal to mu lambda. So if mu is increasing, then lambda will decrease. So ultimately the dimension of the antenna will decrease if we are moving toward the higher frequency sides. So as the frequency to be used are going towards high direction, dimension of the antenna will be small to address the needs of the portable wireless application. And since with the advancement of the MMIC technology, nowadays antennas are low profile, as you all are, I think, from the antenna background. So maximum persons are working in a microstrip patch antenna, which is a low profile antenna. So that is very easy to design. It can fit in any design, it can fit. So what are the expectation of the next generation wireless communication system from the antenna side? That we require that our antenna should be small, because we want a slim mobile which can be put down at the pockets. We require that the radiation pattern should be highly directive, or it should be broadside. It depends on your application, that whether you are designing the antenna for the broadcasting purpose, then we require broadside. If we are using the point-to-point communication, then we require the antenna should be the directive. We require that our antenna should be able to provide the higher gain. Efficiency should be very high. Radiation efficiency should be very high. Gain of the antenna should be high in maximum cases. Only the healthcare system we require the low gain antenna. Otherwise, in maximum communication point of view, we require that the antenna should have the large gain. It should be polarization independent in terms of the transmitter and receiving antenna. So we need the circular polarization, because if we are using the vertical polarization or horizontal polarization, then it is possible due to the wireless transmission, transmitted signal may change its polarization. So at the receiving side, if there is polarization mismatch between the transmitting signal and the receiving antenna, signal can be lost. Another requirement of next generation wireless system from the antenna is that either it should be the broadband or it should be the multiband, depending on the application. So multiband means the same antenna can work for a different frequency band. Like in our mobile, we require at least 5 to 7 antennas. Like for the FM, we require antenna for FM, we require the antenna for GSM, we require the antenna for the Bluetooth, we require the antenna for the GPS. Means for different application, we require the either we can use the one antenna which can cover all the frequency band, or we require the different antennas which can work at different frequency bands. So they will be the lower band bit antenna, but they will provide effective performance at that particular band. So we require that either our antenna should be multi-band, or we require that our antenna should be broadband, so it can cover each band by that antenna. And the most important thing, we require that our structure should be planar, so that it can be integrated with the other devices also. So as we know that the microstrip patch antenna and dielectric resonator antenna both share the advantage of the low profile. So what is the meaning of the low profile? So low profile means the dimension of the radiator in one particular coordinate is very, very small as compared to other. Like if we see the microstrip patch antenna, then microstrip patch antenna, we can say it is a two-dimensional antenna, because its height is very, very small as compared to its width and length. So one dimension is very, very small as compared to other two dimension. That's why it is called a low profile. So both dielectric resonator antenna and microstrip patch antenna have the advantage of the low profile. But as we know that the microstrip patch antenna is easy to design, it can integrate with other systems. So it is most popular antenna in a antenna community. But the disadvantage of the microstrip patch antenna has that since it is made from the metal, so it has conduction losses, it has the ohmic losses, and these ohmic losses are directly proportional with the operating frequency. So as we are increasing the frequency, our ohmic losses will increase rapidly. So at millimeter wave frequency at 24 gigahertz, the losses will be very, very high. So it cannot be used at that millimeter wave frequency or higher frequency. But at lower frequency, it can be used because losses are small, and it can be considered. So dielectric resonator antenna, which is made from the dielectric material, has less conduction losses because it is made from the dielectric material. It is not made from the metal. So it has less conduction losses, and therefore it can provide the better radiation efficiency with the wider bandwidth at microwave and higher frequency. So the dielectric resonator antenna, since it is made from the dielectric material, it has the advantage that, as we know that we can design the dielectric material which has the dielectric constant ranging from 2 to 100. So our resonating frequency of this antenna, our operating frequency of this antenna, will depend on the dielectric constant of that material. So if I'm using the radiator which is made from 10, or if I'm using the radiator which is made from the dielectric constant of 50, while making the other dimensions same, resonating frequency can be changed. So it provides the miniaturization facility that by using the high dielectric constant, we can work at lower frequency. So it provides a high degree of flexibility and versatility, allowing for the designer to suit a wide range of physical or electrical requirements of the varied communication application. Because the as I have mentioned, that the resonating frequency is inversely proportional with the square root of the dielectric constant of the radiator. So we can change the resonating frequency by changing the dielectric material, and that flexibility is not available with the microstrip patch antenna, because microstrip patch antenna is made from the metal, and each metal has some conductivity, and which is almost same. It is in the range of 10 to the power 7. Either we can use the copper or gold or silver or aluminum. So the dielectric resonator antenna is basically made from the dielectric material. So initially, this type of dielectric structures were used as a resonator, and high dielectric constant material were used. Since we know that the high dielectric constant material has the capability to conserve the energy inside the structure, so they are more suitable as a dielectric resonator, not as a antenna. But in 1983, when S.A. Long has experimentally proved that this dielectric resonator structure can be used as a antenna also. So for understanding this concept, we have to see the working of the microstrip patch antenna and dielectric resonator antenna. So that things we will see in next slides. So what are the advantages of the dielectric resonator antenna? As I have told, since it has no less conducting material, that's why higher radiation efficiency. Low radiation Q factor means it can provide the wider bandwidth. It can work from lower frequency, which is 55 megahertz to 135 gigahertz. It has less metallic part, so it has lower surface waves. Design flexibility that I have already mentioned, that we can change the dielectric material, so we can design the antenna for the same resonating frequency by using the different dielectric material. So we have more flexibility, we have more degree of freedom if we are using the dielectric resonator antenna as compared to the microstrip patch antenna. So these are some advantages. It can be used up to 110 degrees centigrade to minus 65 degrees centigrade. So these are some advantages of the dielectric resonator antenna. There are some disadvantages also. So the disadvantages are that it is a not explode as the microstrip patch antenna. You will find the many books for the microstrip patch antenna. You will find many lectures for the microstrip patch antenna. For the dielectric resonator antenna, less literature is available. Theoretical analysis is less developed. Not as low profile as microstrip antenna. Microstrip antenna is it is just like a 2D antenna, but dielectric resonator antenna cannot be say it is a 2D antenna. It is a 3-dimensional antenna because it has a significant height as compared to the microstrip patch antenna. Fabrication is challenging. That is the most main difficulties with the dielectric resonator antenna, that fabrication is challenging. And another challenge is that integration with the circuit is challenging because it is a 3-dimensional antenna. So advanced machinable and easier to integrate materials are needed. But I have mentioned many advantages as compared to the disadvantages. So in future, at millimeter wave frequency, this dielectric resonator antenna can be useful because we do not have any other choice. We cannot use the microstrip antenna at millimeter wave frequency or other higher frequency. So we have to use either the waveguide type of structure, or we have to use this type of dielectric resonator antenna or other types of structures we have to explore. So this is the basic working of a microstrip patch antenna versus the dielectric resonator antenna. So as we can see, in a microstrip patch antenna, metal is placed on the grounded substrate. So this substrate, that means dielectric material, there will be some metals either in a circular shape or rectangular shape, and below this substrate or dielectric, there will be again metal, but it will behave as a ground. Okay, while in a dielectric resonator antenna, this is a ground, this is metal, and above metal, this dielectric material is placed. So it is just opposite to each other. Working methodology is just opposing to each other. In a microstrip patch antenna, metal is placed on a dielectric. Metal is behaving as a radiator, while in a dielectric resonator antenna, dielectric material is behaving as a radiator while it is placed on a grounded substrate. So these are some geometry of which are available. These are the basic shapes: cylindrical, rectangular, spherical, and many other shapes are possible, which are made from the basic structure, either from the cylindrical or rectangular or spherical. And these are some unusual geometry which are proposed by the researchers. So in a dielectric resonator antenna, the modes, analysis of modes or knowledge of modes play very important role. So as we know from our electromagnetic theories knowledge, that basically there can be 3 types of the modes: either transverse electric modes, transverse magnetic modes, or transverse electromagnetic modes. So as we know that for sustaining the TEM modes, we require the 2-conductor system. So in this type of structure, dielectric resonator antenna, TEM modes cannot sustain. So either transverse electric or transverse magnetic modes can be generated or excited inside the antenna, but the beauty of this dielectric resonator antenna is that it supports the hybrid mode also, while the microstrip patch antenna does not support the hybrid modes. Either it can support the T modes or TM modes, but it cannot support the TM hybrid mode. But this dielectric resonator antenna can support the transverse electric mode, transverse magnetic modes, and the it can support the hybrid mode, that is called either TEH mode or TEHE mode. So I'm discussing only the cylindrical dielectric resonator antenna. So in this cylindrical dielectric resonator antenna, there can be TE01 delta mode excitation or TM01 delta mode excitation. So the T01 delta mode, what T represent? T represent that it is a transverse electric modes. So what is the meaning of the transverse electric modes? Means electric field is transverse with respect to the direction of energy propagation, direction of a wave propagation. So suppose if wave is propagation, energy is propagating in Z direction. So the transverse electric mode means the electric field is transverse. It is in a perpendicular to the wave of propagation. It is not along the direction of wave propagation. So in Z direction, there will be no electric field component. Only the magnetic field component can be present. So in this case, when it is T01 delta mode is excited inside the DRA, inside the CDRA, then the magnetic field will be along the Z direction, as you can see by this diagram, blue line, while the electric field will be in a perpendicular or in a transverse plane. And it is not varying with respect to this phi. So this T01 delta mode basically representing the electric field variation in a phi. So since it is a symmetric structure, there is no electric field variation in the phi direction. That's why the this first subscript is 0. 1 is representing that in a radial direction, okay, there is one phi direction, another one is a radial direction, and third one is a Z direction. So this delta is representing the field variation in a Z direction. This 1 is representing the field variation in a radial direction, because we are using the cylindrical dielectric resonator antenna. So it is a we have to use the cylindrical coordinate system. Then there will be rho phi z coordinate system. So there will be some radial variation, there will be some phi variation, and there will be some Z variation. So this T01 delta mode is representing that there is no phi variation. There is one radial variation, half cycle radial variation, when we are moving from center toward the peripheral boundary. And this delta is representing that since the height of the antenna is small as compared to the wavelength, so that's why there is no possibility that there may be some field variation along the Z direction. That's why we use the delta term. So this is representing the T01 delta mode. Since electric field is in transverse direction, magnetic field is along the Z direction. That's why this type of T01 delta mode can be represented as a magnetic dipole. Okay, because Hz is along the direction of wave propagation, that is the Z. Similarly, this TM01 delta mode. So this TM01 delta mode means it is a transverse magnetic modes. So transverse magnetic modes means the magnetic field are transverse with respect to the wave propagation. So there will be no magnetic field component along the wave propagation. So only electric field component will be along the direction of wave propagation. So E field will be there and magnetic field will be in the transverse direction. So this type of modes when it is excited with the cylindrical dielectric resonator antenna, it will behave as a normal dipole, electric dipole. It will behave as a electric dipole. And third type of the modes is called a hybrid mode. So in this hybrid mode, this can be treated as a horizontal magnetic dipole. Okay, this can be assumed that it is behaving like a horizontal magnetic dipole. So the electric field and magnetic fields both are present along the direction of wave propagation. So that's why it is called a hybrid mode, and these hybrid modes are possible to generate in this dielectric material only. So these are some conventional feeding techniques through which we can excite the particular modes. I have told that what will be the field behavior in a transverse electric mode, transverse magnetic mode, or hybrid mode. So particular modes can be excited inside the antenna by placing the feeding techniques appropriately. So as we know that most popular feeding technique is either microstrip feeding technique or coaxial probe, or we can use the slot feeding technique or aperture coupled feeding techniques. So by placing the appropriate feeding techniques at appropriate place, like in just first diagram, if we are placing the probe at this point, that is the close to the boundary, then this type of field will be excited inside the structure, and this type of fields are related with the hybrid mode. So this will excite HE11 delta mode inside the cylindrical dielectric resonator antenna if we are placing the coaxial probe at the boundary. While the same coaxial probe, if it is placed at the center, then this type of field will be excited inside the antenna, and this type of field will excite the TE modes inside the structure. Okay, so either by using the microstrip or slot coupled technique or aperture coupled feeding techniques, we can excite the appropriate mode inside the cylindrical dielectric resonator antenna. So in my work, since we are designing the antenna, and the basic parameters of the antenna are the its bandwidth, its gain, its polarization, and nowadays many other aspects are also very popular, like the phased array or beam forming array, as first speaker has told. So by knowing the basic structure of the individual antenna, or either it is a microstrip patch antenna or DRA antenna, we can move toward the advanced topics like phased array or beam forming array. So we can design the antennas for the 5G communication system, that is for the multiple input, multiple output. But in MIMO system also, you require a one unit antenna. So that unit antenna, you have the command on that particular antenna, either it is a DRA or it is a microstrip patch antenna. So in my work, I had proposed the design of a low profile cylindrical dielectric resonator antenna for the X-band frequency applications. Means first we have to design the DRA antenna for some particular application, that is the 8 gigahertz to 12 gigahertz. Then at the initial, we do not know which feeding technique will be suited. Either you have the option that from the literature you can take the advantage of the former researchers, then you select particular feeding technique without you do some experiments. But in my work, first I have experimented 4 feeding techniques, that which feeding techniques will be suited for my cylindrical dielectric resonator antenna. So I have designed a cylindrical dielectric resonator antenna with the coaxial probe, with the microstrip feed, at the center, at the boundary, and then aperture coupled feeding technique. Then my aim was to enhance the gain and bandwidth of the cylindrical dielectric resonator antenna. By default, this DRA provide very large bandwidth, but if I'm saying that I want the antenna for the whole X band, then it has the very large bandwidth. It is a 4 gigahertz bandwidth. So design the CDRA for the whole X band is a challenging task. So bandwidth enhancement was my task, gain enhancement was my task, and then on the same antenna, I have generated the circular polarization, how we can generate the circular polarization in a particular structure, and then by selecting the DRA as a unit cell, we can design the phased array antenna, means we can move toward the some advanced structure. So that was my work, but I think speakers are ready. So at present, Chandan?
Sir, I am here, sir. I can, if speakers are ready.
Prakash Ranjan sir is ready?
No, sir, he has not joined in.
No, they message me that he is ready. So just a minute, I'm calling to him, and
Okay,
if they
sir.
are ready, then they will continue. Otherwise, I will continue my work. Okay.
Okay, sir.
So dear participant, if you have any question, you can ask. Hana, if I will get time for half an hour in future, then I will continue my work. Just a minute.
Welcome, sir. Good afternoon, sir. Welcome, Dr. Prakash Ranjan, sir.
Good afternoon, sir.
Good afternoon. Can you hear us?
Yeah, yeah.
Yeah, we can hear you, sir. Yeah.
How are you, sir? How is your ear?
Now it's fine. I have taken medicine, but now it's fine.
Okay.
So this one must go on. I can take it, no problem.
Yeah. If you feel comfortable, you can take the session.
No, I will take no issue. But only thing is that I cannot speak loudly. But
Okay.
That's okay. Fine. It's not classroom. It's just a Google Meet,
Yeah.
so we can manage
Yeah.
it. Yes,
Yeah.
sir.
You can take sir, for 1 hour.
Yeah, I will take, no problem.
Okay.
I will try to be as much as possible, but
Yeah.
Please forgive me if I am not able to do that. But I will try as much as possible.
Okay, sir. Thank you.
Shall I start, sir?
Yeah, yeah.
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 Please go ahead. If you allow me, I can start my presentation.
Yeah.
Just
So-
1 minute, sir.
Okay,
Shravan,
Nikum,
you
you are
start.
starting.
Yeah. Yeah. So we are having a great researcher. We have the Dr. Prakash Ranjan. He is currently in the department of electronics in the Triple IT Bhagalpur, and coming to his research interest, he is his research interests are in the field of metasurface, metamaterial absorber, multilayer absorber, and evolutionary algorithm. If you talk about the academic background of Dr. Ranjan, he pursued his B from Anna University in the year 2009. Then he completed his master's in electronics and communication engineering in the year 2012 from YMCA University of Science and Technology, Faridabad. Then he did his doctorate in the field of microwave from NIT Jamshedpur in the year 2019. Dr. Ranjan has one patent titled Zeroth Order Resonator Antenna using slotted metamaterial surface. Then Dr. Ranjan has published 8 publications in reputed journals. Those are SCI journals. Then he has presented papers in reputed conferences. 7 papers he has presented. He has very much efficiently coordinated the setup of antenna simulation lab in NIT Jamshedpur. He also served in various administrative responsibilities in IIIT Bhagalpur, and currently he is having the responsibilities also. He is a reviewer of progress in electromagnetic research. It's a very good journal. Then he has attended multiple conferences and seminars during his work experience. He is also a member of IEEE Technical Society. So I welcome you, sir. With this brief introduction, I would like to take the session, and definitely I hope students will be benefited from such a young researcher which is there with us. Thank you, sir. Thank you very much.
Okay, first of all, thank you, Patel, for such a great introduction of mine. I know I don't know how much I belongs to, but I will try to fulfill your expectations as much as possible. And
Sure,
first of all, I would like to thank all of you, the organizing committee, everyone, Nipun personally, because he has been in touch with me for a long, long time. And from my heartiest congratulations to all of you for organizing such a great sessions, and I hope everyone will get benefited. And so once again, with this word, let me start my presentation. So is it slide visible?
Yeah, it's visible, sir.
Let me make it full screen. I hope it will. Now, is it coming in full screen, or is it still in short form?
Still, it is in the short form, sir. No full screen.
Okay. Okay then. Now, is it in full screen?
Yes, sir. It's okay now, sir.
Okay. So, thank you once again, all of you, for inviting me. As Patel has introduced me, myself, Dr. Prakash Ranjan, I am assistant professor in the Department of AC at IIIT Bhagalpur. Today, we are going to discuss on the topic metamaterial and its application, a soft computing approach. The topic which I have chosen right now is a combination of a metamaterial which literally belongs to the microwave domain, and also the soft computing, where we will especially go for the nature inspired optimization techniques. So we will I will try to at least convince my audience and everyone to apply the nature inspired optimization technique to solve the complicated problem of microwave domain. It's nature is always a great source of inspiration for everyone. We have been inspired from long time, and we have developed a lot of things getting inspiration from the nature itself. Right from the Wright brothers for aeroplane, and today a lot of evolutionary rhythm and nature inspired optimization of rhythms have been developed. That all goes credit to the nature itself. So I will just try, if I able to do that, if I able to convince you that you can take that approach to solve the very complicated problem like metamaterial synthesis, to tackle it, then I will say I will be satisfied at my side that okay, I will able to convince you at certain extent. So this is my email ID and phone number. This is for your future reference. If anybody or anyone of you would like to contact me, you are most welcome. So before going to the technical session, let me I will take this opportunity to introduce my college, ATAL Bhagalpur. We all know it is now it is accorded as a national importance by Government of India. And here I would like to thanks my guide, PhD guide, as well as the director of our institute, Professor Arvind Chaube, for facilitating us, and I have always encouraging us to take seminars. Whenever we go for with this request that okay, sir, we would like to take seminar and presentation, he always with open hand, always ready to bear us with the academic sessions, and he allowed us to take all kind of things. He always firmly believed that the knowledge always comes from sharing. So his vision is always like that, and he always encourages us to share whatever within us. And most of you might have heard that the AAIT Bhagalpur have successfully developed a COVID-19 detection software. The paper they published, it was 96, but right now we have further improved the software up to 98%. Using the CT scan, we will able to detect the corona, and it is at the last stage of the approval, and very soon we will get it approval. And the Siemens company has already has been partnered, and he's going to install the software all over the India in his digital CT scan machines. So we are just the campus is proposed campus. Very soon, within 1 month, the tender has been done. Within 1 month, the construction will start. This will be the computer graphics picture. This will look like, and we will love to see that my campus. This is just near to bank of the Ganga, and we are fortunate to have more than 650 mango trees. So you can imagine how much the campus is greenish campus it is. More than 650 trees means you can imagine like that. And also the Bhagalpur is known for silk city of India. The silk is very famous all over the world. So please come and visit here. Okay, so let's begin this session. First of all, I would like to pay attention on all of you to just pay attention at the spectrum, and why the microwave is so much important to us. Okay, others are always important. Visible spectrum is obviously it is important, but for communication, why microwave is so much important to us? The reason is, if I go for lower frequency than microwave, the ionosphere of our atmosphere, ionosphere layer of the atmosphere will not allow us to communicate with the satellites. It will reflect back. Like radio wave, if you try to have a communication with the satellite, the ionosphere will make reflect. The radio wave will get reflected from the ionosphere. So we will not able to have a communication with our satellites. So that we cannot go for. Similarly, if I try to go for higher frequency, then there is no issue with the ionosphere. The problem is the systems. Till now, we do not have the well-established system which can work on above the microwave like terahertz. So we are bound to work within the microwave. That is the reason the microwave is so much popular. There is no hard and fast to define this range of microwave, but you can say the frequency which is not reflected by ionosphere is termed as microwave and above microwave. So I think, am I audible? Is it okay, everyone? Please, whenever I get problem, please pause to me, and you can text me also. Okay, Nipun?
Yeah, everything is okay, sir. Everything is going fine.
So whenever you feel problem, you just text me, or because right now I cannot see what is going on there. So I'm just looking at
Yes,
my.
sir. Yes, sir. We are here for that. Okay, sir.
So just text me if I get disconnected or anything has happened. You just text me. Okay.
Okay, okay, okay,
Call
sir.
me out. So that is why we are uh, bound to use the microwave, and also it allows us to reduce the antenna size. People who are working with the antenna will know the antenna is basically resonator, right? And all resonators generally has length of lambda. So if you use lower frequency, we will have a larger lambda, and thereby we will have large length of antenna sizes. So in that sense also it helps us to reduce the antenna size, and that is why we are using the microwave. So as I said, the antenna is a resonator. So let's try to have a brief idea what does mean by actually resonance. In one line, you can say if any system behave abnormally at a particular point, that point is a resonance point. Okay. So for example, I would like to take a simple example. This example I have taken from the Dr. Roth of Canada, I think, his lecture. So his credit goes to him only. So this is a very simple example. Say for example, he took a boy sitting on a swing, okay, and the other boy is pushing him. And now we are trying to analyze the system. On one side we are measuring the amplitude, other side we are measuring the phase difference between applied force and the motion. So now you can see when we have very low frequency, then you can see the applied force and the displacement of the person who is sitting on the swing will be on the same direction. Probably there is no phase difference at all. Little bit of there is a difference there, so that's why I'm having the amplitude magnitude non-zero, but mostly it is on the same phase. There is no much difference on the same direction, so on the same phase. But suppose the person who is pushing increase his frequency to 2000 times. So suddenly he is pumping it like a pumping scenario. He just increase his frequency to 2000 times. So that in a 1 second he will push the person in 2000 times. What will happen? So for the first push, you can imagine that the person will go forward and get returned back. But for the second time, he won't get the chance. He will be like the person will not move at all. Just vibrate. The person will start vibrating with the frequency. So in that case, person will not move at all. What does it mean? That means the displacement and the force applied is totally 180 degree out of phase. In between these two, there will be a point where you have the maximum amplitude, and that point will be treated as a resonance. So we have two sides. One side there is a no resonance, also there is a literally in phase, other side is out of phase, but in between we have maximum amplitude. That point we treat as a resonance point. So always the system behave abnormally, we always call it as a resonance. And in the microwave domain, we always look for the resonance. Once a system will resonating, we can extract our desired result from it. If it is not resonating, it is very hard to get the required desired results. Okay. And you will see, you will love to see that how much resonance help us to synthesize the meta surfaces. Now get to the core of the topic, that is meta materials. What is meta material all about? See, the meta is basically a Greek word. It means beyond. Meta is basically Greek word. It means beyond. In the beginning days, people were very much eager to know that what is permeability. After discovering that, they have broadly start dividing the material available in the nature. They have one x-axis as a permittivity and y-axis as a permeability. Now, before going to that, let's give you a brief idea what is permittivity, and just to recall you what is permeability is. Basically, in my sense, it is just a response of the medium. Because if you have two charges, say for example, you have two charges, right? While trying to measure the force between these two, it is now the medium which will decide how much force it is going to now apply on each other. Just if you change the medium, the force will change. That to recall you that F is equal to 1 by 4 pi epsilon Q1 Q2 by R square. That is the formula, right? Now this epsilon is basically permittivity. Now this epsilon is basically a combination of epsilon naught and epsilon r. This epsilon r is basically all depend upon the medium. For free space it is 1, for other medium it may be different value. So this permittivity basically is a response of the medium. This will bring the medium in the picture of the force relation, right? Otherwise the force will be constant throughout the medium. So that is why we treat it as a the response of the medium. The permittivity is similar to the permittivity of for magnetic field. For electric field, it is permittivity, and the same phenomena is true for your permeability. Okay. Now, so this after dividing this 4 quadrant, people divided all the naturally occurring material, and they were surprised to see that there is absolutely no material which lies in the 3rd quadrant of mu epsilon axis. 3rd quadrant means both negative. 1st quadrant means both positive. So naturally there is no such material available in the nature which could give you there is no such material which could give you the mu and epsilon both negative, both at the simultaneously. There are a few materials which one is negative, one is positive. These are some ferrites, some semiconductors are there, but both negative absolutely not available. So people always wait. Yes, is it okay? Now, so that is why the scientists term it as a meta, because it was beyond their reach, right? So if it is not available in the nature, that means you have to made it by yourself. So this, if you made it by yourself, that means it's going to be artificial one. So metamaterial basically is a artificial material which is not available in nature. That's why we are treating it as we are terming it as a metamaterial, and it is artificial one. Now, once if it is negative, then what will be the consequence? What will be the effect of that? So first of all, they if both positive, they term it as right hand material, and if both negative, they also term it as a left hand material. Right and left, just right is the positive left, left is the positive right. So on the same analogy, they trim that like that. So what happens if both becomes negative? So if you recall the solution of wave equation, from there we are driving the refractive index relation, and that it turns out to be a square root of mu epsilon. If you dig out the equation, it's a very small derivation. You just go through it. It is turned out to be a square root mu epsilon. Now, if I try to find out what is the value of square root 4, the right mathematics say it is plus minus 2. Mathematics say it is plus minus 2. But till now, we were not taking the negative side. We always used to take the positive side, and we were working it. But in the case of metamaterial, now we have to take the negative one. And that is why the refractive index is negative now. Because mathematics is a tool. The physics you have to derive from it. So for right-handed, you already have taken positive. So that is why for left-handed, you have to take negative. The consequence of this negative refractive index is that the first is from the Snell's law. Now, we all know Snell's law is mu1 sine theta 1 is equal to mu2 here, where eta 1 sine theta 1 is equal to eta 2 sine theta 2. That is, you know, famous Snell's law, refractive index into sine theta 1 normal from the angle. So when you have eta negative in the second medium, that means the refraction angle is negative. I'm not talking about the reflection angle, but the refraction angle, right? The refraction angle will becomes negative, and that could you see from this animation. You just see the wave. The first medium is the right hand material, whereas the second medium is a left hand material. Now in the left hand medium you can see wave has refracted with the negative refraction angle, not the positive refraction angle. And second thing I would like to pay you guys attention here is that it is just, remember the very famous Michael Jackson dance, that the moonwalk, where the dancer was moving forward, but it apparent that it is moving backward. That is how it is. The wave is propagating, the energy propagating forward, whereas the phase velocity is opposite to the group velocity, and that is why it is termed as the backward wave. Okay, so the left hand media supports the backward wave, and the reason is you can see this is the computer animated one only, but here you can see the difference is very much obviously. Negative refraction, one angle difference. The second one is the phase velocity, you know, is the totally opposite of the group velocity. Now, as I said, the same how to achieve negative refractive index and what are the constituents of that. You see the same formula. Just I have put mathematically on that, and to illustrate you same thing, the right side bottom is picture. Is the picture of a glass filled water with a straw, a glass filled with water with a straw, you know, having a straw in it. In the positive refractive index material, that is the normal water, and the left side is the negative index material. So that will be the look, totally different look will be available. So till now there is no such material available. There is the computer graphics is shown by computer graphics only. It is not available in the you know, it is not available for visible spectra. The people have achieved it for a particular frequency, not for a broad range and not especially for the visible spectra. Now see what is meta surface. So just like any other surfaces, if you are talking about the surface of metamaterial, then we term it as a meta surface. So what is in the normal meaning of surface? The surface of flatness, some kind of flatness nature. So if normal material surface is there, so we also term as the meta surface is nothing but the surface of the metamaterial. Okay. Now lot of you know, the applications has been derived for this meta surfaces, ranges from terahertz to infrared to microwave domain, and now people are very much, and that I will also propose you in the last slides if time permit, to work toward the lower frequency side. So observer, AMC, J2R, antenna reflector, scattering surface, lot of you know, properties, clockings, lot of the applications has been done. So that is what I was talking about, a relation between the normal surface. Let's just try to have a normal surface, relation between normal surface and meta surface. First try to see this normal surface. So normal surface has, you know, periodic arrangement of crystals, atoms, we can say molecules, right? And if it is a pure flat, so this will be the scenario. If it is the pure surface, if the flatness is, the roughness is 0, which is practically impossible to achieve it, but theoretically if it is so, then that will be the scenario, that when you have this, the periodic arrangement of atoms, and that too is a flat, right? So if a person who is trying to achieve the meta surface is also has to arrange its atoms in a periodic arrangement. So from there, the periodicity, the concept of periodicity in meta surface come into the picture. Second, also the concept of unit cell also come into the picture. What is unit cell is here, like here in the normal surface you are having atoms, all atoms are similar atoms, right? In all each and every sense it is similar. So here also you have to have one unit cell which is similar to, must be in periodic, in arranged in 2D manner, right? So from this analogy, the concept of periodicity as well as the unit cell come to the picture. The only thing is that also in atom also the atoms are very small in a strong scale, right? Similarly here also the meta atoms will be very small. Small and large is a subjective matter. So whenever I am saying it is a small, so basically if you are working with a lambda, a particular lambda, with that respect, if it is small, then only I can say it is a small, right? Because a small and large is a subjective matter. So to just have you little bit how does it goes on, the research goes on, just to give one model which was proposed by Drude and proposed by Lawrence, and further it is modified to Lawrence and Drude model for atoms. So he has bring a atom under the influence of electric field, and he compare it with a spring mass system having a damper, right? And with that analogy, he derived the second order differential equation, and after digging out few equations, right, he derived the expression for permittivity. Now I'm not going in detail of it is 3, 4, 4th line for the derivation. I just request everyone to dig out, just go through it, and you will get that. The important the result which we can extract from here is that at resonance frequency, the permittivity is changing. That's the important point. At resonance omega naught, we can have different value of permittivity. Some analogous behavior is appeared, right? So that means with the electric resonance, I can tailor or I can alter the value of permittivity. Now, why I am worried, why I have put this line here, because you see, if you trying to design or derive a metamaterial, your goal is to achieve -1. To make negative, first, a person who is having value positive, you have to change its value. Unless it's not changing, you cannot say that it will get negative value, right? So first, to make him negative, before that you have to change its value, that you alter his value, right? It is just like a person is sitting in a particular place in a classroom, right? If you want to sit another place, you have to first tell him that please stand up, right? That is what it is. So we got a tool that if I able to have a resonance, electric resonance, I can tailor the electric permittivity, right? Similarly, true for permeability also, right? Here also the concept of plasma frequency come into the picture, right? And the role of the plasma frequency is that after plasma frequency, the material becomes transparent at particular frequency. Material becomes transparent after that frequency. So the plasma frequency, the frequency, after that the said material becomes transparent, right? So and before that there will be a reflection, and before that at particular frequency there will be absorptions in the range of that particular frequency, and before that also there will be transmission. So if you say very low frequency, like it will propagate, but after that it will observe, then after it gets reflection, and then ultimately it will have the transmission, right? So the Vesligo was the predicted first for that negative and all. The Pendry, which is the left one, and the Smith at the right one. The Pendry was the first who has practically realized the negative permittivity. Basically, the Sir Pendry was, basically working on this graph, this model. He was working on how to reduce the plasma frequency of a material. It was his byproduct that he got the negative permittivity during his experiment. But now he is a pioneer man. God gave him long life. We all miss him. But he was actually working on negative permittivity. The whole story begins, metamaterial begins in the 1968 when Veslego is a Russian scientist actually. He just gave a prediction about this negative permittivity, negative permeability, and what will be the consequence of that. He first termed the, because during that period there was no such thing available in the nature. There was no, even the theoretical concept was not much developed. So he was simply predicted. Okay, the positive has all the right things. Then if negative will happen, then we have negative phase velocity. Basically, he predicted three things: nothing will change or things will change. That is quite simple, right? It's very, now you are listening, that will very easy to predict. His prediction was two things: one, nothing will change; second, everything will change. What a prediction it is, right? In both cases, he has laddu, right? So that was the Veslego first 1968. He predicted that you will have if you have negative mu absence, then you have negative refracting index, and that might possible that it must be get idea from the square root 4 that plus minus 2 is there. So plus 2 I have already taken, so there is only left negative. So I have to go with the mathematics, and he has predicted that the negative refracting index will be achievable one day. Then it took 30 years to come with a negative permittivity, that is Sir Pendry, and then the same his Smith and all, Selby has further proceeded the work, and the first negative negative refracting index was done in 2001. So it is just a yearly of 20 years way back. A lot of things has been changed, I know. So from there it has started. As I discussed earlier, that the negative permittivity can be achieved, or the permittivity can be altered with the help of electric resonance. So if a person wants to achieve electric resonance, he must have in mind that, okay, I can simply take a simple wire, a lambda wire, it will resonate at particular frequency, thereby it will have a electric resonance because it is a metallic rod, right? Electric field will push the electrons on one side, in the other cycle it will, other half cycle it will in other direction. So it will start, the charge will start oscillating, thereby we will have electric resonance. Similarly, for magnetic resonance, you will have to have a circular ring type of arrangement, right? So flux will, have d phi by dt, certain value at particular frequency, it will resonate, right? So if you have together, both it together simultaneously, that you can say that permittivity and permeability both can be negative. Both can be resonated together, and then it might possible that you will have a negative one. So that is the right side bottom picture is done by Selby. See, Selby, yes, it is Selby work. We saw the first negative refracting index one. So a lot of applications has been, as I said earlier, clocking is a very famous thing, like Hollow Man movie, Mr. India movie, where things becomes invisible. People has been able to achieve a pure clock at particular frequency. That means the wave just go through it without having any phase magnitude difference, thereby lead into pure clocking. So 100% clocking is not obviously theoretically possible, but practically there will be some losses in amplitude. But if you have the same phase, it will have will not be visible to a person, because the things are visible when light get reflected from a particular thing and get reflected to your eyes. So if it is not reflected, if you go through it and with same phase, you will not able to recognize the particular things inside that. So that is the clock. Okay. Perfect lens and our super lens, these are very, where you have inefficient mode of propagation, and very high level of resolution has been achieved from that. phase compensator, that is the very famous in radar applications, where now we have plain wavefront. Till now we were not able to achieve 100% pure wavefront, but now with a pure wavefront, the radar capacity has been increased. Also in the side lobe reduction for horn antenna, these are also done. And very today in my area, because I have worked on the observer and Jaguar antenna, I will show you few works on that metamaterial and Jaguar antenna. So if a person would like to work in this domain, will generally work with the a person who like to work in this microwave domain, he or she has to work with the CST or ANSYS HFSS. This FECO, there is a Trang also software available, is the Indian version of the ANSYS HFSS. CST is FTDD and ANSYS is FEM based softwares. They are all numerical methods, right? So these are the basic softwares we can use for working in the case of and these are few simulations I have put. We will generally do with the BTech students. That is the T, S-plane T and E-plane Ts. VNA and NX chambers are also required for testing purpose. Now, just get the metamaterial transmission line concept. What is that is? So it is the normal transmission line equivalent. If you see R, L, G, C is there. That R refers for ohm per meter, L is the Henry per meter, like that, and G for farad per meter, and G for mho per meter. So that is the primary parameters of the transmission line. So if you say take the lossless case, then you will have C is a parallel, L in the series, right? But and that will treat as a right hand transmission because it is from the right hand media. So for designing the left hand media, we have to have inverse of the same thing. So how can I achieve it inverse? Just replace, in place of inductor put capacitance, and in place of capacitance just place inductance, right? So if you do that, you will have the pure left hand transmission line, right? And as we know from the second order in a solution of wave equation, second order differential equation was there on transmission line also. You can see the beta expression comes from the square root ZSC and YSC shorts, right, series and shunt. So here beta you have positive, right? Whereas for negative transmission, pure left hand transmission line, the beta becomes negative. And that is quite apparent from this expressions, right? Now the problem is the pure left hand transmission line is not possible to achieve practically. Reason is whenever you try to have only series capacitance and there is no parallel capacitance, it is quite next to impossible to achieve, because whenever you put two wires together, either to a strip line or ground plane, it will form a certain kind of capacitance. You cannot ignore it. Or when you have a wave propagate in a line with a certain width higher or lower, it will give an inducting effect, right? From the Kozar book we can refer it. So that lead into that the series inductance and shunt capacitance is unavoidable. It will be there, whether you wish or not. Practically it will be there. So if I try to design the pure left-handed transmission line, because that right side bottom picture where I will put capacitor in series and inductance in shunt, practically it is impossible. Practically you will end up with this kind of bottom picture, where you will have a composite kind of things, where both things are there. So when both things are there, the omega beta diagram will look like that, where for a particular up to particular frequency, especially for the lower side frequency, you will have beta negative. For higher side of frequency, you have beta positive. Now it's very interesting. For certain range, if I am having beta negative, for certain range I am having beta positive. then there must be a point where I will have beta 0. And beta, we all know it is 2 pi by lambda. Beta is 0 means at particular frequency lambda tends to infinity. So practically infinity is not exist. That means infinity means whatever things, whatever the things which we are depending upon lambda is now independent of the lambda, because now lambda is infinity. Whatever you have value lambda length is not have no sense of that, because now lambda is infinity that particular frequency. And using this concept, people determine it as a zeroth order resonance, and using this concept we have derived the antenna, and that antenna is termed as zero antennas. And very, very interestingly, as now things are not dependent upon lambda, now I can have a resonance even beyond much lesser length of the lambda. Now I can have the resonance which is much lower length of the lambda, and that is how we can we are able to achieve miniaturization. One of my friend, he's also in the panel, will take lecture of antenna miniaturization in coming sessions, and I'm very happy. I will very eager to listen him also. He has a very good work in antenna miniaturization, and he will also illustrate you these things that once you have a zeroth order resonance, you will have great level of miniaturization of antenna. So those people who are working in the antenna miniaturization can get inspiration from that. So I think after 2 days his lecture is there. So just to have what is antenna is. So we know all we required antenna to communication. If anything is radiating effectively, then we can term it as antenna. Well, as far as radiation is concerned, everything is radiating. Whether it is a box, desk, anything, you take anything, everything is radiating at certain frequency, at a certain level. But it is up to you at what frequency it is desired for you, and whether it is radiating effectively. That means in terms of efficiency, whether it is acceptable to you or not. Then only I can term it as it is a antenna. So antenna is basically convert requirement for some signal of electromagnetic wave. It just convert your signal into electromagnetic wave, right? So they're not to give you the need of antenna. You just look around you, everywhere there is antenna. Now we also have seen that the routers and Wi-Fi routers, we might have seen that they all have till now also they have 4 and 5 dipole antenna, because now it is a massive MIMO antennas are there. So that is why we have multiple antenna over there, right? So the MIMO, I would say, work on the very basic concept that if one person works can work for 1 unit, then if I take 2%, then my work will be for 2 units, right? So that is on that particular concept only the MIMO antenna works. Simple basics. Okay, a lot of that I'm not going in detail, the receiver diversity, the transmission diversity and all, but that is how it look like. Is any message? Nipun, everything is good? Nipun, is everything
Yes,
good?
Yeah,
Is
it
it
is okay, sir.
for me? But I cannot able to see chat box. So
No, it is okay, sir. You can go ahead.
if it is indirect, please interrupt me, okay? So if you look at the antenna, now requirement is the MIMO, massive MIMO requirements are there. Then you see the routers, like the routers, right? So please mute please mute your microphone. Other people, please mute the mic. Okay, now thank you. So if you see the antenna, there are a lot of antennas are there. That is more number of antenna, and as it look by the picture itself is bulky, right? So we must have a solution of the same. Some kind of solution must be there. By that we can able to remove this bulky size antenna. The requirement of this antenna is that the dipoles are required because it has omnidirectional radiation pattern. That means it radiates equally in all directions. Right? That is the prime requirement of this dipoles, and that is why it is widely used in the case of routers. So the solution is the ZOR antenna. If you have ZOR antenna, it will radiate just similar to your omnidirectional, just similar to the dipole antenna, that is the omnidirectional radiation pattern. That is isotropic in a plane, right? Equally in all directions in a particular plane. That is, it is quite similar to the dipole antenna. If you just like you have put a dipole antenna over there, and it is radiating equally in all directions. So this is the one of the antenna we have worked with us, and you can see this is radiating equally in all directions. Perfectly radiating, it's a simulated one. It is perfectly radiating in all directions. Excuse me. So this kind of antenna will solve this kind of the problem of having dipole on the Wi-Fi router. Very soon you will get a routers which do not have this kind of arrangement. Bulky size routers will be replaced by ZOR antennas. So have a brief, difference between the normal antenna and ZOR antenna is that the normal patch antenna, if you see right-handed, it cannot radiate omnidirectional. It is generally directional, right? And that is why the service area is focused towards the particular site. It's a limited one, right? Whereas once you have ZOR, it radiates omnidirectionally, and you will be happy to have large service area, just like a dipole one, right? The main advantage comes from the fact that once you have the ZOR resonance, that means the wavelength is infinite, and now the structure is independent of its length, width for its resonance. So now you can thought of a resonance which is not much depend upon its length, and that you are not bound to have that particular length. That lambda by 4 must be there. You are now free, and thereby you can have a great level for antenna miniaturization. How to identify that whether you have ZOR resonance or not? So if you look at the patches, then start from the feeding port to the in, it will all have uniform electric field distribution, and that will not case in the case of normal transmission line, or even in the case of your normal patch antenna. As I said, that lambda is infinity now, so you can now relate the permittivity and permeability term to be 0. So it's a great thing. And lot of, as I said, mobile SAR application will become. Till now we are using PIFA antennas and all. So very soon it will be replaced by the equivalent ZOR antenna. In a single mobile, you have a lot of antenna for Wi-Fi, for GSM, for L4 GLT, MIMO. Lot of things are there, right? So now everywhere for all we will have ZOR antenna. Obviously, different antenna will be there, but we will have ZOR antenna replacing all other antennas. These are the few antenna which we have worked and which is the measurement setup. So these are the few one. Now let's talk about the limitation of it. What is the limitation is, you see, when you have a resonance, ZOR resonance, it is at a particular frequency, right? Or for a certain range of frequency. That is why the bandwidth is always limited by the ZOR. So it is always desired to have higher and higher bandwidth, right, for any antenna. So for the same, this is the same requirement for ZOR. So we have proposed a structure which will give enough bandwidth, which will increase the bandwidth, and there you can see the ZOR frequency, the first negative frequency and the second negative frequency, right? And that is what I was talking about. You have the uniform electric field all in the same direction, almost all in the same direction. You can see all electric fields are in the same time, all have the same. Whereas the radiation pattern simulated one, you can see is also omnidirectional, but there is a distortion, there is a at particular angle, it is not 100% omnidirectional, but we can accept it. Now that is all about the JDOR brief one. Now just now try to get inside the absorbers. So absorbers are the basically the thing which can absorb your incident wave. We are fortunate to hear that our sir Jesse Bose was the first who has used this kind of absorber in the oscillator tube to avoid the unwanted reflected from the inside. Basically, cavity whenever you have a certain device and put in a box, the cavity resonance start affecting your devices. So to overcome that, the Sir J.C. Bose was the first scientist to use that kind of observer, and thereby he was successfully able to overcome the cavity resonance. So and so on and so forth. A lot of examples are there. So not wasting much of the time. So some conventionals are, these are the conventional multi-layers or conventional observers, right? Some these are also, you can treat a zoom in a layer, and there's multiple states are placed at lambda by 4 distance, thereby forming a destructive interference, because it will take lambda by 2 to go. I'm talking about the left side service speed screen. You can see it will take lambda by 4 to go and lambda by 4 to come. That way it will travel lambda by 2 distance, and thereby it will have a destructive interference, right? So with that also, but the problem is again same. It all has the narrow bandwidth. Multi-layer observers generally has the wider bandwidth, and the same is true for your pyramid one. These are very famous one, mostly used in anechoic chambers, right? And the advantage that they are very wide band. They offer you very wide band, very wide bandwidth. That is the advantage we can get. But the disadvantage is very fragile, large size. We cannot use an aeroplane for fighter planes and all those places. Or for the device is very, if a device is very small in size, we cannot use that. So let's try to understand the absorption physics. What is mean by absorptivity is. So in order to measure a property of absorptivity, how much a medium can absorb incident wave, we must define a certain parameter. We define it as absorptivity. So suppose some power incident, it is get reflected, and the reflected can be termed as S11 parameter, and the transmission one can be termed as a S21, right? So if that is the case, right, then we can measure the absorptivity as 1 minus mod of S11 whole square minus mod of S21 whole square, where we all know this S11 is in terms of normalized. That is why we are subtracting from 1, right? Now most of the observers are mathematical observers are as such, where you have ground plane as a complete copper, where you are allowed to incident event from top, which interact first with the frequency selective surfaces, then it will interact with the dielectric materials, lossy dielectric materials, and then it will go to the third layer, that is the bottom layer, and that is the copper, pure copper. So with that we have to pass through it, thereby it will get reflected, and that is why we term it as S210. So now you are having absorptivity is 1 minus S1 whole square, right? So once again, to illustrate the benefit of metamaterial observer is that now you are having thinner one. Now the structures are ultra thin, very very small, lambda by 20 in the thickness, right? Now you have narrow band, broad band also, not as much as of the pyramid observer, but now they have the broadband also. The only not give you how to get the idea of
Sir, your voice is not audible.
Yes.
am I audible?
Now it's audible, sir.
Okay, it was failed, right? Whenever this yes, please give me WhatsApp, so I will stop. So I was discussing about the absorption physics. I have discussed it, and then structures. There is no fixed formula where you can apply the formula and I can get there. Few works has been done by IIT Kanpur, Saptarishi Ghosh, and Vaibhav Srivastav sir, that they have designed formula, derived formula for square rings, fixed ring size. So, but that is only for narrow band. So it is again very hard to get for broadband structures, right? So before going to that, let's have a multi-layer observer synthesis problem in our hand. So multi-layer observer is, you can see there are lot of materials has been stacked. Few lot of material number 1, material number 2, material number 3, material number 4 has been stacked. Likewise, to form an observer, and these are widely used in today cases of fighter planes, stealth, all those places is widely used. Only by 230 only. Can I extend, Nipun, can I extend little bit to 245? Can I go up to 245?
Okay, sir, but next session has to be started at 3 p.m.
So okay, I will try to finish by 245. So
yeah, 2:45. Then we can start next session at 3:15. At least half an hour required per participant for lunch.
Okay. So let me move forward and fastly. So basically, designing this kind of multi-layer observer is basically optimizing problem. Why it is so? Because in one hand you want to have very thinner structure, other side you also want to have very less reflected wave, and that is because for these two are opposite to each other. Where in one place you want to minimize its dimension, otherwise you also want to have minimize the reflection. So these two are contradictory to each other, and that is why it is an optimizing problem where you have to have a balance where you have optimum level of thickness and as well as reflective wave. So that is done by I will show you a few results after a few slides based on that. Second, in the case of metamaterials design synthesis, the problem is that where if you see the impedance at a particular frequency, if you see the expression, the wave gets inside the metamaterial only and only if there is no hindrance in terms of impedance. That means that free space impedance and the impedance of the particular metamaterial structure must be same. Otherwise, from we all know that if there is an impedance difference, there will be reflectivity, and wave will get reflected. There will not be absorption, right? But to do that, you see mu and epsilon must cancel each other. Then only we will have z omega is equal to eta naught. That is, eta naught is a free space impedance, right? Now that is here itself you can see the role of your metamaterial concept, because it is the metamaterial who give you the idea that with the resonating structure material you can alter the value of mu and epsilon. So if it alter in such a way that the relative part, the imaginary and real part both becomes equal to each other, then it becomes cancel out, and thereby you will have perfect absorption, right? So you can see random structures has been proposed till now. I have put few examples of that flower shaped structure. How can you derive expression for flower shaped structures? Like, so this concept is, this concept of synthesizing the structure is very tough. You have to do lot of hit and trial methods to achieve a particular structures, right? Like one of the applied physics paper is that ascent coin shape. The right side topmost picture is a Chinese author, and the paper title was the ascent coin Chinese civilization. Can you imagine? How can I get the formula for the same? To derive the, with my MTech and BTech students generally ask me, sir, is any formula to get the dimension of the same? I said simply say no. Till now, no. You have to derive it. You have to do the lot of fit and try. So this method of synthesis is very tough. But still, we have done few results. So you can see, I'm just making forward fast one. So we have achieved few structures which are very working very fine. So you can see, again you can see the normalized impedance and mu epsilon. That is what I am talking about. Here you can see within the range of absorption, the mu and epsilon real part is same to each other. Similarly, imaginary part is also same to each other. After that, it becomes deviate. Its value is not equal to each other, but within the range of absorption, it is almost equal. So the band of absorption was 5.94 to 11.92, right? 5.98 gigahertz bandwidth. So that you can see here, within that range, it is approximately equal to each other. Other than that, it is not equal to each other. Again, but time is not there, so I could not go for these things. But you can see, this is how we fabricate it. Once fabricated, this is the zoom view I have put here. This is the sheet we fabricate. We put in front of transmission antenna, and there is a two antenna setup attached with the VNA, and then we measure the reflectivity. That is how we measure it, right? And this is the completion of practical and measured one. So this is C. But if you ask me, sir, is any formula to derive this W1, W2? I would say so, no. It has been done with the hit and trial. I'm very openly telling you, it is done with the hit and trial method. So this is the disadvantage of this problem, right? To overcome this, we have adopted some soft computing optimization technique. So as I said earlier also, the nature is a great source of optimization, great source of inspiration. From that only, we have taken the particle sum optimization technique. Some that is the wind-driven optimization technique also, which is inspired from the motion of air passing in the atmosphere. Particle sum optimization techniques are inspired from the movement, the searching of food from the swarms, that is the birds. Okay? So let us move forward a little faster, so that I have brought a lot of things to, but as Nipun said, so let's go through this is the simple PSO I have brought. How does the velocity works and how the expression works. The only thing is that I'm going to tell you. You see, all the dots are all dots are nothing but the birds in a field. In a search space is nothing but a ground where all these are words, right? Bird will move towards the next motion of the word will be towards such way that it will keep record of its own availability of food. Also, the other one which get the best food, and he will move in that direction only. So you can see the dark brown color where we have the best food or the minimum one or maximum one of the function. These are the points in the search space representing the points or birds in the analogy case where the birds are looking for that point. But it will move in a such way that the net motion will be equivalent to its own best as well as from the other one. It also inspired from the other person who has got the best food till now. So its own motion will be depend upon other as well as its own motion, its own based. So that is why it termed as G based and P based, and its initial velocity also. So you see, slowly all the birds will accumulate at a particular point. When a person get when you after having certain iteration numbers, when you have the desired result, they all will get at the particular point. Okay, leave that. So now get back to the synthesis of multi-layer observer. You can see this is the cost function, which we have little work. We have to improve that, and now we have got actually till now what we have seen that the multi-layer observer they have proposed for particular case like TE 15 degree, TM 45 degree. They have proposed for particular case only, but we have clubbed all those together, and thereby what we have proposed is this is working very fine for wide range of applications, right? So you can see minus 10 dB for different range, 0.5 to 5.5, 2 to 8, and likewise you can see lot of, and that what we have convergence graph also over there. Now let's discuss about the binary wind driven optimization technique. You see, till now the WDO was proposed in 2013 and 14 by Barakat. He proposed for continuous value problem, but we modified it to suit it for binary version. And why we do need for binary version is, I will let you know in very soon. You can see the reason is, as I said, our job is to synthesize a structure which can resonate at particular frequency, right? But we do not want to follow the hit and trial method. So what we did, we taken a particular area, we term it as a unit cell structure, and we designed this structure such a way that it is resembling in terms of pixels. We designed the structure in terms of pixels, where a 0 where there is no copper, if 1 means there is a copper. So a random structure is basically depending upon, if I go for like from row towards column like this way. So this is 1 2 3 4 5 5 5 5. So it's just a vector variable which is 10 only a binary value, right? It is a variable which is in forms of matrix, or you can say a simple linear vector which you can divide in terms of matrix, right? So our synthesis of a particular resonating structure or desired structure has been converted into a simple optimizing a binary vector. Now the problem is how to optimize it, because till now what we had the optimization techniques were only suited for continuous value. But I need a vector optimization technique which must work only for binary, must work for binary vector, that is 0 and 1, because now my variable as such it can only take 0 and 1, because that is how my problem is. If I take 0, I will say there is no copper, right? So for that, to show you better, here is the structure. You can see the yellow color is is representing the presence of copper, whereas 0 represents absence of copper, and thereby you can generate a resonating structure. Now you can see the whole structure has been divided into 256. With the help of symmetricity, we have converted 256 to only 36 variable. We want less number of variable because optimizing less number of variable is easier than optimizing large number of variable, right? For that, the problem is, in that case, now you have, suppose you have a binary version of optimization technique, but how does a structure behave, that will be totally decided by a FEM solver or FDP solver, that is HFSS, or you may have that CST. But your optimization technique is generally working with your MATLAB. So we have written your code in MATLAB of optimization technique. Other side you have the HFSS. So that's why you need to have a link between that. So it's required a lot of VB scripting to interface these two, so that I could give the command through MATLAB and it will run in HFSS and get the output to the MATLAB once again then only it will able to, because then only it will able to know that how does a random structure behave. And based on that, your optimization technique will move forward. Because suppose you have a randomly 30 dimension, so in a one go it will generate 30 random structures. Now which structure is behaving in which manner, this will be totally decided by your FEM solver, and there I need this kind of interfacing. Right now, as I said earlier, this 256 has been converted into only 36, and thereby it lead to lot of very much good results. Like I would say you, this kind of structure, I will show you few 5 or 6 results to you. These are the multi-point results. You have to put the cost function such that it only count the peaks, and thereby it will it will give you the maximum number of peaks. So during early days, I got 5 and 6 peaks examples. So you can see this has been already published one. So you can see the seat, fabricated seat. Here you see the 5 one, this is the 5 band, and this is the 6 band. But the unit cell, you can see, I have not driven any hit and try. I simply give the cost function to the optimization that I need maximum number of peak, and it turned out to be after taking 7 days of running continuously, they give me the best one is the 6 band, and it was this result, which I fabricated on and ended by working very fine. We have also tested it. Similarly, in case of wideband also, we in place of measuring number of peaks, we start measuring the bandwidth. Once we start measuring the bandwidth, now the optimization mode try to improve your bandwidth. Obviously, it is obviously the band of working, the all depend upon how much unit size line length you are taking, how much thickness you are taking, which material you have taken. This all are dependent, but now you are free from the optimization. Now you are free from the hit and try method. By simply utilizing the optimization technique, you can solve this problem. These are the few examples. Also, apart from the observer, few examples of AMC, where AMC reflect you right with a 0 phase. Reflect you the wave with a 0 phase, right? And the bandwidth terminal is plus minus 90 degree. So that is how few AMC examples are there. Single band AMC. This is generally if you talk with the guys, antenna guys, they will use it to suppress the interface, right? Some dual band, right? Now, so these are the few examples I have showed you. This all have been derived using this simple interface. So you need one binary optimization technique, other you need interfacing of these two. Now with this setup, it might possible that you will get the result, but it might possible that you won't get the result. There are cases where we fail to achieve a single band itself because we have not taken the desired the unit cell size in that range. We have not taken the thickness in that particular range. So after overcoming lot of obstacle in the beginning, but once you start getting the result, you will have lot of beautiful results, and that all credit goes to the optimization techniques. So here you can see nature-inspired optimization technique successfully overcome a synthesis problem of metamaterial or metamaterial based structures. Now the problem with this technique is that the problem is it required very large computing, because you can imagine, suppose you have 30 particles, right? 30 particles, and if you go for 100 or even 50 iteration, right? So now you can imagine how much it's going to run, 30 into 50 times plus 50 all. So that much times it is going to run the HFSS software. Now, if a single HFSS runs for 20 minutes, now you can calculate the duration, how much it takes to complete a cycle of 50 iterations. Generally, I have seen that it is much more than the 50 iterations it took to get a good result. So in that sense, it has one drawback, but it will overcome your so-called hit and trial method. Because in the hit and trial method, we don't know how much, whether we are going to get it or not. But here, now you are free. You just need to give the command. You just need to have a proper cost function. You just need to have all the basic setup on a place. You just need to have very good computing power with yourself, and then it will give you the good result. I skipped a few things like PS and all. So keeping the limitation of the time, I have left all those things. So you can see all those things again. That was this, multi-binary structures, wide binary structures. See, it's working very fine. I have not drawn all those graphs like a new epsilon. It is similar. All the cases have shown very good responses, right? Then at last, I would like to talk few things what we are working in this days right now. In the case of microwave domain, lot of works has been done, but the terahertz and lower frequency side, these are the two area one can thought of, one can work on that area, and we are also working that nowadays in working that area, which is untouched till now, or very less number of work has been done in that area. So if you go to lower side frequency, less than 0.5 gigahertz or less than 1 gigahertz frequency, if you work in that range, then in that side also very much required. Lot of applications are there. If you work in the terahertz, lot of sensor applications are there. You can work on that. Then right now we are working also to optimize a ZOR antenna based on the same principle, which the tool which we have developed using the pixel active structure and designing a ZOR antenna which work fine for wide band of applications. Also, as I discussed earlier, nature is a great source of inspiration. We also trying to develop our own nature inspired optimization techniques, and we are very much verge of getting one. And we will maybe in future we will meet, we will discuss one new nature inspired optimization technique. So I urge everyone to watch National Geographic, see some behavioral journal, nature behavior journal, to get inspiration from there. You will love to see that lot of optimization techniques can be derived from there only. Also, we are very much eager to, because now we have a lot of optimization techniques, but we are looking for a problem which we can solve it. So that is why that area also we are looking at. So the audience, it's my request, if anybody has any problem where I can apply my optimization techniques, you guys are most welcome. Please feel free to contact me. Antenna array synthesis is the problem also. Till now, a lot of theoretical work has been done, but nowadays it is applying in the case of 4G LTE and E-node Bs. Intelligent node Bs are there. The best BTS now terms at E-node Bs. In the case of 4G LTE and 5G, now it terms as E-node Bs. In case of 4G, now you are going to have a tower in sitting, in every streets, rather than having a city. So in that case, you have massive MIMO. Now you have an array. So antenna array synthesis will be there, and that there also you can apply nature inspired optimization techniques. Now, we are international. We are working very till now. Very recently, we have done a MOU with the Carter University, Malaysia, where we are working. The mechatronics department, me and all guys are working to optimize the bleed of the wind turbine, because when a wind turbine rotates with different velocity of air, you need to tilt the blades, optimize the blade such that it will give the maximum output. So very recently we have done MU. Lot of other academic activities also going to be taken place. We are also on the verge of completing another MU with the National Polytechnic Institute of Mexico. In the Katin in Malaysia, there is a Professor Das. He's an alumni of IIT Guwahati. So he's the person with whom we are in touch. Then we are having Professor Hernan. Actually, he always object me, sir. Whenever I say Hernan, he said, no, you say pronounce Hernan, because in the Spanish we would never say pronounce H. So the Professor Hernan is there, with whom we are very much. We have till now we have once again working with the multi-layer observers practically also. Some few optimization techniques we have developed together, and which will be under the we have communicated very recently in Mathematica. Some multi-objective black V2 optimization techniques we have communicated very recently. DMSRT is the lab of DRDO at Kanpur. Here also the work on observer is taking place. That I cannot say how much what kind of work, but we have applied for one kind of project over there. So we are expecting one project from there. So hope for the best, and let's see. And we all have collaboration work with the IITs and IITs and IIITs. A lot of works are there. So and we are open for PhD MTechs. We have started taking the PhD admission and MTech. So and also in collaboration, we are very much happy if anybody get a work in collaboration for you guys. Any one of you will be willing to try to get any help from us. We are very much open. With these words, let me conclude my session. And because it was I have brought a lot of things, but unfortunately I suffered one accident where my eyes was ear was paining. Still I have taken medicine, so I was not able to have a lot of things. I have joined late. Sorry for the same. And it might possible that when we meet next time, we will have a lot of other things to discuss. So here I am open for your any questions, sir.
Thank you very much, sir, for your nice movement from very basic of the microwave, why microwave, to a very great thing that you all have done, and that is like a kind of new optimization technique. So I would like to request the participants, if anyone is having any doubt, you can ask.
You can ask anything if you wish. Please, sir, go ahead.
So there are some questions, sir.
Yeah,
if
please.
You allow, I can read from chat box.
Okay. Let me see. I haven't seen the chat box, so because it was my presentation was open, so let me check it. Okay. Let me go from the top. Okay, good afternoon. Please, the recording is okay. Preparing.
Excuse me, sir. I will read out, sir.
Okay, please go ahead.
Sir,
Yeah,
one
please.
question from Srenik Sade. If you provided the cut slot in the radiating patch, then how to find out the loss and total electric field?
See, that is what I am telling. My approach was not to go theoretically, not to go much inside the theoretically. My approach is always to go simpler. So suppose we all know generally when we make a cut, generally we make for extend the bandwidth, right? So when we make a cut, generally it introduces a capacity effect, right? Now, how does it affect the radiation pattern? How does it affect your losses and all? That's another issue. But my job is to make a cut in such a way that it might fulfill my fulfill my desire, and thereby I have used that. If you look at the case of my optimization, generally a pixel is nothing but a kind of cut on a complete sheets. I have not shown the response, the result which we are getting in the JDOR. If had I brought here, I would have able to explain it better. That in the case of JDOR, when we are trying to make a pixel cut, right? The one thing we are getting is the broad response, but the results. The problem is that we are losing the very unique property, that is the omnidirectional radiation pattern. It loses from the omni towards the directional, but giving the large bandwidth. So there is a trade-off between these two. There is a one side bandwidth, there is another side is one. There is a one side bandwidth, another side is a JDOR response. So what we are observing is a trade-off between these two. So we have to take one of that.
Thank you, sir. The last question is, I think it will be taking time. Sir, can you explain the one optimized algorithm step by step for one shape?
Yes, I have. See, if you look at my slide, I have brought ESO, and I have brought step by step only. I have brought full slide. I will share it, not, but I will give the lecture note for the same. Where there is a dry run.
That's what I was to say, sir. If Mr.
No, that
P.
is.
Narayan Rao, if he wants to contact you,
Yeah, I will. Please mail me. I will send you the test I will refer. You see, I have brought this function. Can you see my function?
Yes.
yes, sir.
Find a maximum of the function. You see, I have brought it step by step only. Step by step only. I brought it. I was supposed to explain it step by step only, but as Nipun said rightly, because I joined late, that is why I could not able to do that. I have to skip it. Right? I have brought it. The whole concept, why the role of velocity, why does we update it, what is the value of C1, C2. I brought everything here, but I skip all those things to save my time. Okay. And also I have not explained much of the WDO and how to achieve the binary version of the same. I skip all those things. So better, at least that way, you will feel to contact with me, at least for in that way also.
Yes, sir. Yes, sir. That would be very good help, sir, from your side. We'll definitely share the materials to students.
Yeah, I will send it. No problem. There are papers are also there, but I will send the one. There is a good thesis of the same where each step by step has been done.
There is a question, sir.
Okay.
How to deal losses at terahertz?
Yeah.
Which material can be selected for dielectrics for terahertz?
See, I am telling you, forget about the things which are good for them. For the first thing, what is things is available for you. The thing is that IIT Chennai has very good fabrication as well as the Kanpur. So they have few materials which will share you. I forget his name. They will share you. On that you can, because once you have terahertz, the size of fabrication is very less. In that small scale of fabrication, you cannot do with a simple PCB machine. In the microwave domain will give you flexibility that you can do the fabrication in mm scale, right? Because of the microwave domain, you can do fabrication in mm scale. So generally, I used to take simple PCB machine is available in our lab. We used to simply fabricate it. But when it comes to terahertz, we cannot go with a simple PCB machine. So all the directories which are available, like FR4, Dwyer, these things we cannot use it. The dielectric you have to take such that which we can fabricate. Otherwise, there is no means of no meaning of taking all the things. So please contact the Kanpur and IIT Chennai. They have the good fabrication and some DRDO lab. They will give you the list of materials which they can fabricate, and thereby you can use it.
I think, sir, questions are done.
Thank you.
So Sir, after your injury also you are
What is
here
it?
with us.
Just Narayan Rao, one last line I would say. How to export and import MATLAB and HFSS, two different entity. You just do one thing, that ask the HFSS to save your result in a text file, and with the file command you can read that exported result from the HFSS, because HFSS don't know about anything about MATLAB don't know anything about HFSS. It is the text file which can work in between these two, and some scriptings are there. You can go to GitHub, you will get the interfacing scripting are available. Lot of my also contributions are also over there. Go to GitHub, you just put up MATLAB HFSS interfacing, you will get all the these scriptings. You just need to have a little bit of modification because it is VB scripting, and you will get the result. If you have help, if you feel any problem, please contact me. For my phone number, it is available in the website. You can go and take it. Yes, optimizing in MATLAB and implementing in HFSS. Yes, that is what we are. The HFSS is the different entity which solve the structure, random structure, where optimization is running in the MATLAB. So you need to interface these two. Optimization is always work in the MATLAB because there you are writing the codes. HFSS is totally different entity. You have to just interface these two. Have a Google, and there is a scriptings are there. You just type it, scriptings, HFSS, MATLAB scripting. You will get that. GitHub you will get, sure.
So with this, I just want to say thank you, sir. With your injury also, you came here and give such a elaborated lecture, and you started from your microwave, your concept. Then you just very much appreciated concept of swing that you shown for the resonance concept. That is, I think everybody will appreciate that concept. And then you smoothly take transition from that resonance to metamaterial and meta surfaces. Then you also explained how transmission line model is changed for negative refractive index materials. Then the very good concept that you told, how you will get the that omnidirectional kind of structure with your ZOR antenna. Then the very interesting part that you have touched, and I think many of our researchers will definitely contact you, and they will definitely ask us for your mail IDs and contact numbers. Based on this analysis that you did, that optimization technique, you have done wonderful work in that area. And from PSO WDO to binary WDO, that was a very good concept. And then you also give some ignition to the students, to the candidates, that you can at least start working between the interface of MATLAB and HFSS. Yeah. So that kind of ignition you have already put on some researchers. So we are very happy to have with such a great kind of inventor, we can say to you, sir. So many things you have done by yourself, and thank you, sir. Thank you very much. Thank you, sir.
Thank you, sir. Thank you, sir, for your nice and informative session on metamaterial. Even some medical emergency, you came and you joined the session, and
there, so
you presented very nicely. And sorry for that, we are running actually short of time.
Yeah, that is what also I feel. Lot of audience is also asking. I have brought everything, but I could not able to show you. Sorry for the same from my side also, but
actually we have to start. Yeah. Actually, we have to start third session at 3 p.m.
Thank you, all of you.
But if we will get some time, then we will let you know.
Okay, thank you. Yeah. Thank you, everyone.
Thank you, sir. Thank you very much. Thank you, sir.
Dear participants, as per schedule, the third session has to be started at 3 p.m. but now it is 2:57 p.m. So for getting the lunch, we are taking the break of half an hour. So we will join at 3:30. Because many participants have joined since 9:30, 9:15. So we are taking the break of half an hour. So we will meet once again at 3:30. 3:30 session will start. So you are requested to take the lunch and join at 3:20 so that session can be started at time at 3:30. And thank you very much for joining.
Thank you, participants. We'll meet at 3:20.